Hello there and welcome to Physics with William, where curiosity gets cozy and science takes the scenic route to somewhere calm, quiet, and hopefully a little closer to sleep. Tonight we're turning our attention toward the brightest object in our sky, the one star so familiar that we often forget it is a star at all, the sun. It rises, it sets, it warms our faces, fades our curtains, wakes the birds, powers the weather, grows the grass, and occasionally ruins a perfectly good afternoon when you forget where you park the car and every metal surface has become a small oven. We know it so well in daily life that it can feel almost ordinary, just a glowing circle above us, dependable and distant, sitting there in the blue like a cosmic lamp. But the sun is not a lamp. It is not a quiet ball of fire hanging politely overhead. It is a deep, layered, restless sphere of plasma, magnetism, heat, pressure, motion, radiation, and mystery. And the more carefully we look at it, the stranger that familiar golden disk becomes. Tonight's question sounds simple at first. What is above and below the sun, really? It almost sounds like something a child might ask while lying in the grass, watching the clouds drift past. Above the sun, perhaps space. Below the sun, perhaps more space. And in one sense, that is true. The sun floats in space, surrounded on every side by the wide darkness of the solar system. But the question becomes much richer when we slow down and look carefully. Above the sun could mean above its visible surface, where its atmosphere rises into a thin, blazing halo that stretches far beyond what our eyes can normally see. It could mean the corona, the solar wind, the magnetic loops, the invisible river of charged particles that sweeps past the planets and eventually reaches the edge of the sun's influence. Below the sun could mean beneath the visible surface, inside the glowing body itself, where light takes an astonishingly long and complicated journey outward from the core, where matter is squeezed into conditions so extreme that ordinary intuition has to quietly leave the room and perhaps make itself a cup of tea. There is something wonderfully odd about asking what is above and below a sphere in space. On Earth, above and below feel obvious because gravity gives us a direction. Above is where the clouds are. Below is where the floor is. If you drop a biscuit, below is where you sadly find it. But in space, the sun does not have a top and bottom in the same everyday way. It rotates. It has poles. It has an equator. It has a north and south in a technical sense. But there is no cosmic ceiling above it, no basement below it, no tidy attic where the spare comets are stored. Direction depends on where you are standing, or floating, or orbiting. If you were on one side of the sun, Earth would seem to be on one side of it. If you were on another side, Earth would appear somewhere else entirely. The sun does not sit on a shelf in the universe. It is part of a moving, turning, orbiting system, and our usual sense of up and down begins to wobble as soon as we leave the ground. So before we wander above the sun's surface and below its bright face, we have to gently loosen our earthbound habits. We're used to thinking of the sun as being above us during the day, but from the sun's point of view, Earth is just one small world, orbiting through space, sometimes on one side, sometimes another, always falling around it in a long, graceful curve. We look up and see the sun, but the sun is not really up. It is outward from Earth, along the direction where our patch of the planet happens to be facing. Later, when Earth turns and your part of the world faces away, the sun does not go down in any absolute sense. We simply rotate away from its light. Sunset is not the sun sinking. It is the ground beneath your feet gently turning you into shadow. That is both less dramatic and somehow more beautiful, though admittedly it does make the phrase watching Earth rotate into evening a little less catchy than sunset. And because this is a sleepy little journey through science, let me ask you something before we go farther. Where are you listening from tonight, and where is the sun for you right now? Has it already slipped beyond the horizon, leaving your room in evening quiet? Is it morning where you are, with light coming through the curtains and the day just beginning to gather itself? Or are you somewhere in the deep middle of the night when the sun feels less like a blazing star and more like a memory waiting on the other side of the planet? It is a nice thought, really. All of us scattered around Earth, each turned toward or away from the same star, each living under a different angle of its light. Some people are waking under it, some are working under it, some are hiding from its heat, some are waiting for it to return, and all of us, whether we notice it or not, are tied to it by gravity, warmth, biology, time, and an ancient rhythm older than every human story. If you find this kind of quiet science soothing, or if it helps your thoughts slow down after a long day, I would be very grateful if you liked the video and subscribed. It helps this calm little corner of the universe reach other tired travellers who might enjoy drifting through space without having to put on a spacesuit. And do not worry, there will be no sudden dramatic countdowns, no urgent alarms, and no expectation that you stay fully alert. In fact, if you drift away before we get to the inner layers of the sun, that is perfectly acceptable. The sun has been shining for a very long time. It will not mind waiting. To begin, picture the sun as most of us first understand it. A bright disk in the sky. It seems flat because it is far away, like a coin of light placed against the blue. Of course, we know it is a sphere, but even saying sphere does not quite prepare us for what kind of object it is. The sun is so massive that it contains almost all the mass in the solar system. The planets, moons, asteroids, comets, dust, spacecraft, and everything else orbiting it are, by comparison, a small leftover scattering. Jupiter is huge by planetary standards, but even Jupiter is only a modest companion beside the sun. Earth, with all its mountains, oceans, cities, forests, storms, volcanoes, libraries, sandwiches, and unresolved email threads, is a tiny speck in comparison. And yet from our perspective, the sun appears about the same size in the sky as the moon. That coincidence is one of the reasons total solar eclipses are so striking. The moon is much smaller than the sun, but also much closer, so it can briefly cover the solar disk and reveal the pale outer atmosphere normally hidden by glare. During those moments, what is above the sun becomes visible as a soft, ghostly crown, spreading outward like delicate white hair around a darkened face. That outer glow is one clue that the sun does not end where our eyes think it ends. The visible surface, the part we usually see, is called the photosphere. It is not a solid surface like the crust of Earth. You could not land on it, walk across it, or leave footprints there, though any attempt would end badly long before footwear became relevant. The photosphere is more like the layer where the sun becomes transparent enough for light to escape into space. Beneath it, the gas is so dense and opaque that light is constantly absorbed and scattered. Above it, the gas thins and photons can travel outward toward Earth, crossing the distance in about 8 minutes. When sunlight touches your skin, it has just finished that final clean run across space, but its earlier history inside the sun is far less direct. Some of that energy began in the core and wandered outward through a dense interior in a slow, staggering path, bouncing and being reabsorbed again and again before finally escaping. Sunlight feels immediate, but in a deep sense it carries a very old story. Below the visible surface, the sun is organised into regions that behave differently. At the centre is the core, where pressure and temperature are high enough for nuclear fusion. This is where hydrogen is transformed into helium, releasing the energy that supports the sun against gravity and eventually becomes the sunlight that warms our world. Above the core lies a region where energy works outward, mostly through radiation, passing from particle to particle in a long, patient process. Farther out, in another region, vast currents of hot plasma rise, cool, sink, and rise again, carrying heat by motion. Near the visible surface, this churning creates a grainy texture that telescopes can observe, like countless bright cells appearing and shifting across the sun's face. The sun may look smooth from Earth, but up close its surface is alive with motion, like boiling soup on a scale that makes every kitchen comparison feel a little underqualified. Above the photosphere, the sun keeps going. There is the chromosphere, a thinner, reddish layer that becomes easier to see during eclipses or through special filters. Above that lies the corona, the outer atmosphere, which is strangely and famously hotter than the visible surface below it. That detail has bothered scientists for a long time in the productive way that mysteries bother scientists. Usually we expect things to get cooler as we move away from a heat source. If you stand near a fire, your face is warmer than it would be across the room. But the sun's corona does not follow that simple expectation. The photosphere is hot, certainly, but the corona reaches temperatures far higher. The reasons involve magnetic fields, waves, reconnection, and the transfer of energy through plasma, all of which we will approach carefully rather than throw at you like a basket of complicated laundry. The corona is not just a pretty halo. It expands outward and becomes the solar wind, a stream of charged particles flowing away from the sun in all directions. This wind moves through the solar system, brushing past planets, shaping magnetic environments, feeding auroras near Earth's poles, and forming a vast bubble around the sun called the heliosphere. In that sense, what is above the sun is not merely empty space. It is the beginning of a great invisible atmosphere that extends far beyond the orbit of Earth, beyond the orbit of the outer planets, out toward the boundary where the sun's influence meets interstellar space. We live inside the sun's extended environment. Not inside the bright ball itself, thankfully, but inside its magnetic and particle-filled reach. Earth is not simply near the sun. Earth is immersed in a region made by the sun. That can be a humbling thought. We often imagine space as emptiness between objects, but the space around the sun is active. It carries particles, radiation, fields, dust, and signals. The sun breathes into the solar system. Not with lungs, of course, but through constant outflow and occasional eruptions. It releases flares, blasts of radiation from active magnetic regions. It launches enormous clouds of plasma called coronal mass ejections. These events can race across space and, if directed toward Earth, disturb our planet's magnetic field. Sometimes the result is beautiful, as curtains of aurora shimmer in high-latitude skies. Sometimes it is inconvenient, affecting satellites, radio communication, power systems, and astronauts who would very much prefer space weather to remain polite. The sun may seem calm on a warm afternoon, but it is not a passive light bulb. It has moods, cycles, storms, and magnetic knots that twist and snap. Still, the sun is not chaotic in the sense of being random beyond understanding. It follows physical laws. It rotates, though not like a solid ball. Different latitudes rotate at different rates because the sun is made of plasma rather than rock. Its magnetic field becomes wound up and reorganized over an approximately 11-year activity cycle, during which sunspots become more or less numerous. Sunspots appear dark only because they are cooler than their surroundings, not because they are cold. They are regions where intense magnetic fields interfere with the normal flow of heat from below. Around them, loops and arcs of glowing plasma can rise into the solar atmosphere, tracing magnetic structures larger than planets. Imagine looking at a glowing thread that could swallow Earth many times over, and then remember that this thread is not string but plasma, held in place by magnetism. The sun has a talent for making everyday words feel too small. Below the sun, if we mean beneath its surface, lies the machinery that makes all of this possible. Gravity pulls the sun inward. Fusion in the core releases energy outward. The two are balanced in a long-lasting stability. This balance is not stillness, but a steady relationship. The sun is not exploding apart because gravity holds it together. It is not collapsing inward because energy from fusion provides pressure. For billions of years, that balance has allowed the sun to shine with remarkable steadiness. Not perfectly steadiness in every detail, because the surface and atmosphere are active, but steady enough for life on Earth to depend on it. Every tree, every crop, every ocean current shaped by solar heating, every weather pattern stirred by uneven warmth, every morning that begins with a light, all of it rests on that balance deep below the visible surface. This is where the question becomes more than astronomy. What is above and below the sun is also what is above and below our ordinary experience of daylight. Above the sun, there is a vast atmospheric reach that connects our star to the planets. Below the sun, there is a deep engine that turns mass into energy and sends light outward. Around the sun, there is motion. Within it, there is pressure and transformation. Beyond it, there is the galaxy. And from Earth, there is us, looking up, giving directions like above and below to a star that gently refuses to fit inside those words. The sun also has a place in the larger structure of the Milky Way. It is not at the centre of the galaxy, not especially large, not especially small, not young, not ancient, not alone in the grand sense, and yet it is everything to us. It orbits the galactic centre with the rest of the solar system, carrying Earth and all the planets along. So when we say Earth orbits the Sun, that is true, but not the whole picture. The Sun itself moves through the galaxy. The planets follow, not as a neat flat classroom diagram fixed in place, but as a moving system travelling through a much larger stellar city. If you imagine the Sun as still and the planets as circling around it, you have a useful first sketch. If you imagine the whole system drifting around the Milky Way, you begin to sense the layered motion we are part of. You are sitting still perhaps, or lying comfortably. But Earth is rotating. Earth is orbiting. The Sun is moving around the galaxy. The galaxy itself is moving within a larger cosmic flow. Stillness, like up and down, depends very much on your point of view. That does not make our everyday view wrong. It makes it local. And local views matter. From the ground, above and below are real enough to keep us from bumping into furniture. Sunrise and sunset are real enough to guide sleep, work, prayer, farming, travel, and memory. But science often begins by honouring the local view and then gently stepping beyond it. The sun above the horizon becomes Earth, turning toward a star. The visible surface becomes one layer in a deep plasma system. Empty space becomes a flowing solar environment. Up and down become questions of gravity, rotation, and perspective. What seems simple becomes rich. What seems familiar becomes almost impossible to take for granted. So tonight, as we begin this slow journey, we will not treat the sun as a flat disk in the sky or a simple ball of fire. We will treat it as a place, though not a place we can visit in any ordinary way. We will move in thought from the bright face we see to the atmosphere above it, then down into the hidden layers beneath it. We will follow magnetic fields as they rise and loop and break. We will drift outward with the solar wind and think about the region of space shaped by the sun's presence. We will widen the view until our star becomes one moving member of a galaxy filled with other stars, and then we will return, as we always do, to Earth, where sunlight lands softly on windowsills and reminds the body what time of day it is. For now, hold the image gently. The sun is not just above you, it is around you in influence, beneath your daily rhythms, behind the weather, inside the food you eat, written into the chemistry of life and present in every ordinary patch of daylight. It is not close in the way a lamp is close, but it is intimate in its effects. Your skin knows it, your eyes know it, your sleep cycle knows it, every green leaf knows it. The sun is distant enough to be safely observed from 93 million miles away, yet close enough that a cloudy day can change the mood of a city. That is quite a relationship for something we often reduce to a yellow circle in the corner of a child's drawing. And now that we have loosened the question a little, now that above and below no longer feel quite so simple, we can begin to look at the sun not as it appears from one quiet spot on Earth, but as a moving star in space, turning, travelling, and carrying its family of worlds along with it through the dark. The sun feels steady because our lives are built around its regularity. Morning after morning it appears, or at least the daylight does, and evening after evening it leaves us again. It gives us the impression of a dependable object fixed at the centre of our daily pattern, as if it were waiting calmly while Earth does all the moving. We wake, work, eat, rest, and sleep under a rhythm that seems so familiar it becomes almost invisible. The sun rises over rooftops, crosses the sky, and sinks beyond the horizon with such ordinary grace that it is easy to forget the truth. The sun is not sitting still. It has never been sitting still. Not for 1 second. Not even in the quietest sunrise you have ever watched. Not even when it looked perfectly balanced on the edge of the sea. Not even when it seemed frozen in a winter sky like a pale coin above the trees. That impression of stillness is one of the great tricks of perspective. From Earth, the sun appears to move because our planet rotates. We turn beneath it, and that turning creates the daily sweep of sunlight across the sky. But once we step outside that everyday viewpoint, the situation becomes much livelier. Earth spins, Earth orbits, the sun rotates, the sun moves through the galaxy, the entire solar system travels with it, and the galaxy itself is not resting either. Everything is in motion, nested inside larger motions, like a set of dances happening at once. We do not feel most of them because they are smooth, continuous, and shared by everything around us. Your chair moves with Earth. Your room moves with Earth. Your cup of tea moves with Earth. Even the biscuit you may have misplaced is participating in a grand cosmic journey, though admittedly without much awareness of its responsibilities. When people first learn that Earth orbits the sun, it is often presented as a clean picture. There is the sun in the middle, round and bright. There are the planets arranged around it, each following a path. It is a useful image, and for many purposes it works well. But it can quietly suggest that the sun is fixed in place like a lamp in the centre of a room, while the planets circle dutifully around it. In reality, the sun is also moving, and the planets are moving with it. The solar system is not a clockwork display sitting on a table. It is more like a moving caravan, held together by gravity, travelling through the wider city of the Milky Way. The planets orbit the sun, yes, but the sun carries the whole system along as it travels around the galactic centre. This motion is not a small detail. It changes how we picture our place in space. The sun is one star among hundreds of billions in the Milky Way, and it orbits around the galaxy centre in a vast path that takes hundreds of millions of years to complete. Human history is a blink beside that journey. All of recorded civilization, all our cities, languages, wars, inventions, recipes, lullabies, clocks, calendars, and arguments about who left the lights on have occurred during a tiny fraction of the sun's galactic orbit. The sun was moving through the galaxy before Earth had humans, before Earth had flowers, before Earth had animals with bones, before Earth had anything that could look up and wonder where the light was coming from. It will continue moving long after every person listening tonight has become part of the deeper history of this planet. The speed involved is enormous by human standards, though again, we do not feel it. The sun moves around the Milky Way at a tremendous pace, carrying Earth and the other planets along with it. We are not being left behind because gravity binds the solar system together. The planets do not trail after the sun like loose balloons. They remain in orbit around it, each following its own path while the whole system moves through galactic space. This is why the simple flat picture of planetary orbits is only part of the story. The planets are not drawing circles around a motionless point. They are tracing paths around a moving star, and that moving star is following a much larger path of its own. It may be tempting to imagine the planets making corkscrew trails behind the sun as it moves through the galaxy. That image can be visually appealing, and it does capture the idea that our orbits are part of a larger motion. But it can also mislead if taken too literally. The real geometry is more subtle. The planets orbit in a plane that is tilted relative to the sun's path around the galaxy, and the sun's motion is influenced by the gravitational structure of the Milky Way. The solar system is not like a neat train rushing forward with planets spiralling behind it in a perfectly tidy pattern. Space rarely arranges itself for the convenience of diagrams, but the central point remains true. We are moving with the sun through the galaxy, not circling a star that is fixed to the cosmic floor. Even the sun's own body is not still. It rotates, but not in the way Earth rotates. Earth is a solid planet, at least in its outer form, so its surface turns as one body. The sun is made of plasma, a hot, electrically charged state of matter, so different parts of it can rotate at different speeds. Near its equator, the sun turns more quickly. Near its poles, it turns more slowly. This difference matters because the sun's magnetic field is embedded in its moving plasma. As different latitudes rotate at different rates, magnetic field lines can become stretched, twisted, and tangled. Over time, this contributes to the sun's magnetic activity, including sunspots, flares, and great looping structures that rise above the visible surface. So the sun is moving through the galaxy, rotating around its own axis and churning inside. It is a star in constant internal motion. Beneath the visible surface, hot plasma rises and cooler plasma sinks in enormous circulating patterns. These currents help transport energy outward from the interior. Near the surface, they create a texture that can be seen through solar telescopes, a pattern of bright cells where hot material wells up and darker edges where cooler material sinks back down. From Earth, the sun may look smooth and featureless to the unaided eye, which you should not stare at directly, of course, because eyes are useful and deserve kindness. But observed safely with proper instruments, the sun is textured and restless. Its face changes, features appear, shift, and fade. Spots emerge and rotate across the disk. Bright regions flare. Magnetic loops rise and fall. The calm golden circle is really a seething, structured, active star. The sun also wobbles in a sense because the planets tug on it. We often say that planets orbit the sun, and that is mostly true in everyday language, but more precisely, the sun and planets orbit their common centre of mass. Because the sun is so much more massive than everything else in the solar system, that centre is usually very close to the sun, sometimes even inside it. But the massive planets, especially Jupiter and Saturn, pull enough that the sun does not sit perfectly at the exact centre of the solar system. It moves slightly in response to the gravitational influence of its planetary companions. This wobble is not a sign of weakness. It is simply gravity being mutual. The sun pulls on Jupiter, and Jupiter pulls on the sun. Earth pulls on the sun too, though much more modestly, like a polite request compared with Jupiter's firm handshake. This idea is more than a curiosity. Astronomers use similar wobbles to discover planets around other stars. A star with an unseen planet may shift slightly because the planet's gravity tugs on it. By measuring that motion, scientists can infer the presence of worlds too faint or too close to the star to see directly. So our own sun's subtle dance with its planets is part of a broader method for finding solar systems across the galaxy. The motion of a star can reveal the hidden companions around it. A tiny stellar wobble can whisper, "There is a planet here." The sun's path through the galaxy is shaped by the combined gravity of the Milky Way. The galaxy is not just a flat, bright band in the night sky. It is a vast rotating system of stars, gas, dust, dark matter, and a central region around which everything moves. The sun lies in one of the galaxy's spiral features, far from the centre, in a region that is neither the crowded heart nor the lonely edge. As it orbits, it also moves slightly above and below the main plane of the galaxy, over very long timescales. This means the sun does not follow a perfectly flat track. It has a gentle vertical motion relative to the galactic disk, rising and falling across immense stretches of time. Here again, above and below become relative words, but they still help us picture the sun's journey through the Milky Way's broad starry structure. There is something comforting in realizing that our star is ordinary in some ways and remarkable in others. It is not the biggest star, Far from it. There are stars so large that, if placed where the Sun is, they would engulf the inner planets. It is not the hottest star, nor the youngest, nor the oldest. It does not dominate the galaxy. It is not at the centre of everything, and yet, for us, it is the central star, the gravitational anchor of our world, the source of nearly all the energy that sustains life on Earth. Its motion through the galaxy does not make it less important. It makes it part of a larger story. The Sun is not a throne, it is a traveller. The fact that we do not feel this motion tells us something important about motion itself. People sometimes ask why, if Earth is spinning and orbiting and moving with the Sun, we are not swept away or dizzy all the time. The answer is that we are moving along with Earth smoothly, and motion at a constant speed is not something we feel directly. What we feel is acceleration, changes in motion. In a car travelling steadily on a smooth road, you may barely notice the speed unless you look outside. But when the car brakes, turns, or bumps over a pothole, your body notices immediately and may file a complaint. Earth's motions are large, but they are steady enough that we experience them as normal. Gravity holds us to the surface. The atmosphere moves with the planet. Our bodies, houses, oceans, forests, and beds are all part of the same moving system. This is why stillness can be local rather than absolute. You may be lying completely still right now, breathing slowly, perhaps under a blanket, perhaps with one foot mysteriously outside the blanket because the human body has complicated temperature politics. In your room, you are still. Relative to the ground, you are still. But relative to Earth's axis, you are rotating. Relative to the Sun, you are orbiting. Relative to the Milky Way, you are travelling with the Sun. Relative to the wider cosmos, you are part of even larger motions. None of those descriptions cancels the others. They are all true from different frames of reference. Physics does not always replace one truth with another. Sometimes it gives us a stack of truths, each useful at a different scale. The Sun's movement also affects the region of space around it. As it travels through the local interstellar medium, the solar wind flows outward and forms a vast bubble of influence around the solar system. This bubble moves with the Sun, pressing through the thin gas and magnetic environment between stars. It is not a solid shell, but a boundary region where the outward flow from the Sun meets the wider galaxy. Space around the Sun is therefore not merely an empty stage. It is a moving environment shaped by the Sun's radiation, magnetic field, and particle outflow. The solar system has weather in the broadest sense, and it has a kind of outer edge where the Sun's breath gives way to interstellar conditions. Spacecraft have helped reveal this picture. Some human-made machines have travelled far enough to pass beyond the main influence of the solar wind and enter interstellar space. They are tiny, silent messengers moving away from the Sun, carrying instruments and records of the civilization that built them. Their journeys remind us that the solar system is not a closed room. It is an open region in a galaxy, and the Sun is moving through that galaxy with its family of worlds. The farther we send our machines, the more clearly we see that the Sun's domain has structure, boundaries, and motion. There is another kind of movement worth noticing, and that is the Sun's change over time. It is stable on human timescales, but it is not unchanging. Stars are born, live, evolve, and eventually die. The Sun formed from a cloud of gas and dust billions of years ago. It settled into the long main part of its life, during which it fuses hydrogen in its core and shines steadily. Over immense time, its brightness slowly changes. In the distant future, it will exhaust the hydrogen fuel in its core and enter later stages of stellar evolution, swelling and transforming before eventually leaving behind a dense remnant. This is not a danger for tomorrow or next year or any human planning calendar. It belongs to deep time. But it reminds us that sitting still is not the Sun's nature in any sense. It moves through space, turns on its axis, churns inside, shifts magnetically, and evolves across cosmic ages. The Sun's magnetic cycle gives us a more immediate example of change. Over a repeating span of years, solar activity rises and falls. At times, sunspots become more numerous. Flares and eruptions become more likely. At other times, the surface appears quieter. This cycle is tied to the sun's magnetic field, which reorganizes itself again and again. The magnetic poles effectively reverse during the cycle, and the sun begins building toward the next phase of activity. This is not like a clock with perfect mechanical precision, but it has a recognizable rhythm. The sun has seasons of magnetism, though not seasons like Earth's spring and winter. Its activity breathes in and out over years, and Earth feels some of the effects through space weather. When solar activity increases, the sun can release more energetic events. A flare can send radiation across space at the speed of the light. A coronal mass ejection can hurl billions of tons of plasma outward. If such an eruption is aimed toward Earth, it can disturb our magnetic field after travelling across the space between us. The result may be bright auroras, sometimes visible farther from the poles than usual. The same disturbance can also affect satellites, navigation, radio systems and power grids. Modern civilization depends on technologies that reach into space or rely on precise signals from it, which means the moving, changing sun is not just an object for astronomers. It is part of the practical environment in which we live. Yet even with all this motion, there is a deep steadiness too. The sun's core has supported its light for billions of years. Its gravity has held the planets in their paths. Its energy has given Earth a relatively stable source of warmth across the history of life. Motion does not always mean instability. A heartbeat is motion. Breathing is motion. Ocean currents are motion. The turning of Earth is motion. The sun's restless activity exists within a larger pattern of endurance. It is dynamic, but not reckless. It changes, but not so wildly that life on Earth could never adapt. The sun is both restless and reliable, which is perhaps why it can feel so ordinary and so astonishing at the same time. If you watch sunlight on a wall, it may seem still for a moment. A pale rectangle rests on the floor. Dust drifts through it. Nothing dramatic happens, but that quiet patch of light is part of a chain of motion. It began as energy released in the sun's core. It moved outward through the solar interior. It escaped from the visible surface. It crossed space while Earth turned and orbited. It entered the atmosphere, scattered and softened, passed through a window and landed in your room. The source of that light was rotating, churning, magnetically shifting, and travelling around the galaxy the entire time. The stillness was real in your room, but it was only one layer of the story. The same is true when we say the sun rises. It is a useful phrase and there is no need to retire it. Science does not have to make language stiff and joyless. We can still say sunrise and sunset. We can still say the sun is high or low. We can still enjoy the golden hour without muttering corrections at the horizon, like a disappointed textbook. But behind those everyday phrases, there is a deeper view. Sunrise is Earth turning you toward the sun. Noon is your part of Earth facing more directly toward it. Sunset is Earth turning you away. The sun itself is rotating, moving, and carrying the solar system along a galactic path. Every day is therefore not only a local turning but a small moment in a much larger voyage. This larger voyage is difficult to picture because our minds evolved for nearby things. A thrown stone, a falling branch, a path through trees, a stream, a hillside, a fire. We are good at understanding motion we can see and feel. Cosmic motion is too vast, too smooth, too slow, or too fast depending on the scale. The sun's galactic orbit takes so long that no human civilization can watch even a meaningful fraction of it directly. Its rotation is easier to observe with instruments, especially by tracking sunspots, but still not something the unaided eye can safely follow. Its internal churning is inferred through careful observation and physics. Its subtle wobble due to planets requires precise measurement. The sun's motion is everywhere, but it is rarely obvious to casual sight. That is one reason astronomy is so humbling. It teaches us that reality is not limited to what feels immediate. The ground feels still, but it turns. The sun looks like it crosses the sky, but we rotate beneath it. The sun seems fixed at the center of a diagram, but it moves through the galaxy. The solar system seems like a set of orbits drawn on paper, but it is a moving gravitational family. Our senses are not foolish. They are local instruments, tuned for survival on Earth. Science adds other instruments, other viewpoints, and a willingness to let familiar pictures become larger. So when we ask what is above and below the sun, we cannot imagine a stationary star with neat directions attached to it. The sun is rotating, so its north and south poles have meaning. It has an equator, and it has regions above its visible surface where atmosphere and magnetic fields extend outward. It has layers below that surface, where energy travels from the core towards space. But the whole object is moving, and that motion changes the way we should picture the scene. Above the sun is not a fixed ceiling. Below the sun is not a fixed basement. There are directions relative to its surface, its rotation, its magnetic field, and our viewpoint. There are also directions relative to the galaxy. The words remain useful, but only if we treat them gently. This is a good place to linger for a moment, because it prepares us for the next part of the journey. If the sun were a solid, motionless object with a simple edge, then asking what lies above it would be straightforward. But the sun is not solid, not motionless, and not simple at the edge. Its visible surface is only the layer from which light escapes most easily. Above that surface, the solar atmosphere rises into increasingly thin but intensely active regions. Magnetic fields arch through it. Plasma follows those fields. Energy moves in ways that are still being studied. The outer atmosphere reaches temperatures that seem surprising compared with the surface below, and eventually that atmosphere flows outward as the solar wind, filling the solar system with the sun's presence. The sun is therefore not sitting still, and it is not ending neatly either. It turns, travels, trembles, breathes particles into space, and carries Earth along through the Milky Way. Our world is not orbiting a static lamp. It is travelling beside a star with its own motion and life history. And as we let that picture settle, the next question becomes easier to approach. If the sun is so active, and if its visible surface is only the bright layer we happen to see, then what exactly lies above that surface, in the glowing atmosphere that surrounds our moving star? Above the sun, there is no quiet emptiness waiting politely for the light to end. There is no clean border where the star simply stops and space begins, like the edge of a painted circle on a wall. What we see from Earth as the sun's surface is only the beginning of a much larger, stranger environment. It is the bright layer from which most visible sunlight escapes, but above it, rising outward into space, the sun has an atmosphere. It is thin compared with the blazing material below, but it is not gentle in the ordinary sense. It is threaded with magnetism, shaped by motion, stirred by waves, heated in puzzling ways, and stretched so far outward that Earth itself moves inside the sun's extended influence. The solar atmosphere is not a decorative glow around a star. It is an active region where the sun reaches beyond its visible face. When we think of an atmosphere, we usually imagine something like Earth's air. We think of clouds, wind, pressure, weather, and the invisible mixture of gases we breathe without noticing most of the time. Earth's atmosphere fades gradually with height. It does not end at a hard line either, though we often draw boundaries for convenience. Climb a mountain and the air becomes thinner. Rise higher, and it becomes thinner still. Eventually, satellites move through regions where there are only scattered particles, but even there, Earth's atmosphere has not vanished completely. It has simply become so sparse that it no longer behaves like the air we know near the ground. The sun's atmosphere is similar in one broad sense. It also fades outward gradually, but almost everything else about it is more extreme, more luminous, and much less friendly to picnic blankets. The sun's atmosphere begins just above the photosphere, The visible layer we normally call the surface. That word surface can be misleading, because the sun is not solid. There is no crust, no ground, no place where a spacecraft could rest and admire the view while unfolding a little metal chair. The photosphere is more like a glowing fog layer, where the sun becomes transparent enough for light to escape. Below it, photons are jostled and absorbed and scattered by dense plasma. Above it, the material becomes thinner, allowing light to stream outward into space. This is the layer that gives the sun its familiar disk, the bright round face that dominates the daytime sky. Above the photosphere lies the chromosphere. The name means coloured sphere, and it comes from the reddish glow that becomes visible during solar eclipses or through special observing instruments. On an ordinary day, we do not see the chromosphere because the photosphere is overwhelmingly bright. It is like trying to notice a candle flame next to a searchlight. But when the main disk is blocked during a total eclipse, or when telescopes isolate certain colours of light, the chromosphere reveals itself as a thin, active layer above the visible surface. It is not smooth or still. It is filled with jets, spikes, arches, and small eruptions. It flickers with structure, as if the sun's edge were covered in restless, glowing grass made of plasma. One of the most striking features of the chromosphere is the presence of spicules. These are narrow jets of plasma that shoot upward from the lower solar atmosphere and then fall back or fade away. They are short-lived by solar standards, but they are enormous compared with earthly things. Imagine columns of hot material rising thousands of miles above the sun's visible surface, appearing and disappearing in great numbers. If Earth had weather like that, umbrellas would need a serious redesign. Spicules may help carry energy upward into the outer atmosphere, though scientists are still studying exactly how much they contribute and how they interact with the magnetic field. They remind us that the sun's atmosphere is not a passive blanket. It is constantly exchanging material and energy with the layers below. The chromosphere is also a region where the sun's magnetic field becomes especially important. Plasma is not ordinary gas. It is made of charged particles, and charged particles respond to magnetic fields. This means solar material can be guided, trapped, lifted, and shaped by invisible magnetic structures. Through special telescopes, the chromosphere can appear filled with streaks and filaments, many of them tracing the direction of magnetic fields. These fields act like a hidden framework, not rigid like iron bars, but influential enough to organize the motion of the plasma. Where the magnetic field is concentrated, the atmosphere can become especially active. Where field lines twist and reconnect, energy can be released suddenly. The sun's atmosphere is therefore not simply hot gas above hotter gas. It is a magnetic landscape. Above the chromosphere is a transition region where the temperature changes sharply. This region is thin compared with the size of the sun, but physically it is fascinating because it marks a sudden shift between the lower atmosphere and the outer corona. The material becomes more rarefied, and the temperature rises dramatically. This is one of the places where the sun begins to challenge everyday expectations. If you move away from a fire, you expect the air to grow cooler. If you move upward from Earth's surface, temperature changes in complicated ways, but you do not expect the upper atmosphere to become millions of degrees hotter than the ground below. Yet above the sun, that is what happens. The outer atmosphere, the corona, is far hotter than the visible surface. The corona is perhaps the most famous and mysterious part of the solar atmosphere. During a total solar eclipse, when the moon covers the bright disk of the sun, the corona appears as a pale, pearly halo extending outward into the darkness. It can look delicate, almost soft, like faint white streamers brushed around the black circle of the moon. But that gentle appearance is misleading. The corona is incredibly hot, highly structured and constantly changing. It is so thin that it would not feel hot in the same way a dense object does, because there are very few particles to transfer heat. But the particles that are there are moving with enormous energy. Temperature in this sense describes the motion of particles, and in the corona those particles are moving very fast indeed. This creates what scientists call the coronal heating problem. The The visible surface of the sun is hot, but the corona above it is much hotter. That is unexpected if we imagine heat simply leaking outward from the interior. Something must be delivering energy into the corona and heating it. The leading explanations involve magnetic fields and waves. The sun's surface is constantly churning, and that motion can shake magnetic field lines, sending waves upward. Magnetic structures can also become twisted and stressed, until they suddenly rearrange, releasing energy into the surrounding plasma. This process, called magnetic reconnection, is one of the key ideas in solar physics. It is like the sun's magnetic field sometimes ties itself into tense knots, and then snaps into a new arrangement, converting stored magnetic energy into heat and motion. Magnetic reconnection is also central to solar flares. A solar flare is a sudden release of energy in the sun's atmosphere, often associated with active regions where magnetic fields are especially strong and complicated. Flares can release radiation across the electromagnetic spectrum, from radio waves to visible light to X-rays. They can brighten dramatically in minutes. From Earth, the sun may look calm, but instruments observing it in different wavelengths show flashes and bursts that reveal its changing magnetic power. A large flare is not merely a bright patch. It is a sign that the sun's atmosphere has rapidly reorganized energy on a scale that makes most human explosions seem like a polite cough in another room. Sometimes, magnetic activity launches even larger events called coronal mass ejections. These are huge expulsions of plasma and magnetic field from the corona into space. A coronal mass ejection can carry an enormous amount of material away from the sun, moving outward through the solar system. If one is directed toward Earth, it can interact with our planet's magnetic field and produce geomagnetic storms. These storms can make auroras brighter and more widespread, which is the beautiful side of the story. They can also affect satellites, power grids, communication systems, and navigation signals, which is the less beautiful but very practical side. In other words, events above the sun can become events in our technological lives. A storm on the sun does not stay politely on the sun. The corona is not uniform. It has holes, loops, streamers, and active regions. Coronal holes are areas where magnetic field lines open outward into space rather than looping back to the sun. From these regions, solar material can escape more easily, contributing to faster streams of solar wind. These holes can appear dark in certain types of ultraviolet or X-ray images because they are cooler and less dense than surrounding coronal regions. They are not holes in the sense of empty pits. They are regions of open magnetic structure, places where the sun's atmosphere is connected more directly to space. The word hole is useful, but like many words in astronomy, it should be held carefully and not taken too literally. Coronal loops are among the most visually striking features above the sun. These are arcs of glowing plasma following magnetic field lines, rising from one part of the solar surface and returning to another. They can tower above active regions and persist for hours or days, changing shape as the magnetic field evolves. Some loops are larger than Earth, some are far larger. They reveal the invisible magnetic architecture of the solar atmosphere by making it glow. Without the plasma, the field would be hidden. With it, we can see great luminous curves rising above the sun like bridges made of fire, though not fire in the ordinary chemical sense. The sun is not burning like wood or coal. It is plasma radiating energy from processes rooted deep in its core and shaped near the surface by magnetism. Prominences are another dramatic feature. These are enormous structures of relatively cooler, denser plasma, suspended in the corona by magnetic fields. Seen against the dark background of space at the edge of the sun, they can appear as bright reddish loops or curtains. Seen against the bright disk, they may appear darker and are often called filaments. This difference in appearance is simply a matter of viewpoint. The same structure can look bright at the edge and dark against the face. It is a reminder that solar features, like many things in life, depend heavily on background and perspective. A prominence can stretch for vast distances, quietly suspended until magnetic changes disturb it. Sometimes it remains stable for a while, sometimes it erupts, lifting away from the Sun and becoming part of a larger outflow. Above the Sun, then, is a layered and magnetic atmosphere, but it does not stop at the corona. The corona expands outward into the solar wind. This is a continuous flow of charged particles moving away from the Sun in all directions. The solar wind carries part of the Sun's magnetic field with it, shaping a vast region around the solar system. Earth moves through this wind all the time. Most of it is deflected by our planet's magnetic field, which forms a protective bubble around Earth. Without that magnetic shield, the solar wind would interact much more directly with our atmosphere. Even with the shield, some charged particles are guided toward polar regions, where they collide with atmospheric gases and create auroras. Those shimmering curtains of light in northern and southern skies are not just pretty displays. They are visible signs of a connection between Earth and the Sun's outer atmosphere. The solar wind comes in different speeds and densities. Some streams are faster, especially those associated with coronal holes. Some are slower. When fast streams catch up with slower material ahead of them, they can create disturbed regions in space that affect Earth's magnetic environment. The solar wind also changes with the solar cycle. During times of greater activity, the Sun releases more eruptions and its magnetic field becomes more complex. During quieter times, patterns of solar wind may become more stable. Space around Earth is therefore not a still vacuum. It is a changing environment influenced by the Sun's atmospheric behaviour. It is strange to realise that what is above the Sun can shape what happens above Earth. The two atmospheres are very different, but they are linked across space. A magnetic disturbance on the Sun can send energy and particles outward. Days later, Earth's magnetic field may tremble in response. Auroras may glow. Satellites may experience increased drag or electrical issues. Radio communications may be disrupted. Astronauts may need protection from increased radiation. The Sun is far away, but its atmosphere reaches us through light, particles, and magnetic structure. The distance is enormous, yet the connection is real and continuous. To understand the solar atmosphere, scientists observe the Sun in many kinds of light. Visible light shows the photosphere and sunspots. Hydrogen light reveals structures in the chromosphere. Ultraviolet and extreme ultraviolet observations show hot plasma in the transition region and corona. X-ray observations highlight very energetic regions. Radio observations reveal other processes in the atmosphere and solar wind. No single view tells the whole story. The Sun is like a complex piece of music, and each wavelength lets us hear a different instrument. In visible light it may seem calm. In ultraviolet it becomes a landscape of loops and flashes. In X-rays, active regions blaze. In radio waves, storms and particle events leave their own signatures. The solar atmosphere is not hidden because it is absent. It is hidden because our eyes are tuned to only a narrow portion of what the Sun is doing. Space missions have transformed our understanding of this region. Observatories watching from Earth orbit can monitor the Sun continuously, without the interruption of night or most weather. Some spacecraft study the solar wind directly. Others travel closer to the Sun than any previous machines, sampling particles and magnetic fields in regions that were once only inferred from afar. These missions have shown that the corona and solar wind are highly structured, with switchbacks, waves, turbulence, and complex magnetic behaviour. The closer we look, the less the Sun resembles a simple glowing ball, and the more it resembles a vast natural laboratory for plasma physics. One of the reasons the solar atmosphere is so important scientifically is that plasma is the most common ordinary state of matter in the visible universe. Stars are plasma. Much of the gas between stars is ionized. Many cosmic environments are shaped by magnetic fields and charged particles. By studying the Sun, we study a nearby example of processes that occur throughout the universe. The Sun is close enough to observe in detail, close enough for spacecraft to measure its outflow, close enough for changes to affect Earth. It is our local star, but it is also a guide to stellar behaviour more broadly. Above the sun, we see not only solar weather, but a sample of cosmic physics. And yet, for all the scientific intensity, there is something quietly graceful about the solar atmosphere. During an eclipse, when the corona appears, many people describe a sense of awe that is difficult to capture. The sky darkens, the temperature may fall, birds may quiet, the familiar sun is covered, and suddenly the hidden outer atmosphere appears, pale and wide, surrounding the moon's dark silhouette. For a few minutes, the ordinary star becomes visibly strange. What was always there is revealed only because the brightest part is blocked. It is a lovely reminder that brightness can hide as much as it reveals. The photosphere gives us daylight, but its glare conceals the corona from our everyday eyes. The solar atmosphere also reminds us that boundaries in nature are often gradual. We like edges. They make things easier to draw and name. The surface of a table, the wall of a room, the shore of a lake. But stars are not built for our preference. The sun's visible edge is an optical effect, a place where transparency changes. Above it, the atmosphere thins but continues. The corona becomes the solar wind. The solar wind fills the heliosphere. The heliosphere extends far beyond the planets. Eventually, the sun's influence blends into the interstellar medium. Where does the sun end then? At the photosphere, where visible light escapes? At the outer corona? At the boundary of the solar wind? At the edge of its magnetic influence? The answer depends on what we mean by the sun. A star is not only its bright sphere, it is also the environment it creates. This matters for the original question. What is above the sun, really? If we stand in imagination just above the visible surface, above means the chromosphere, with its reddish glow and needle-like jets. Higher still, it means the transition region, where temperature rises rapidly. Farther outward, it means the corona, hot and thin, shaped by magnetic loops, holes, streamers, prominences, flares, and eruptions. Beyond that, above becomes the solar wind flowing through the solar system. And if we keep going, we find that the sun's atmosphere has become a vast bubble of influence surrounding all the planets. In that sense, Earth is not merely below the sun in our sky, or beside it in orbit. Earth is inside the extended outer atmosphere of the sun. That thought can make daylight feel different. The sunlight entering your room is not the only sign of the sun's presence. Invisible particles stream past Earth. Magnetic disturbances ripple through space. Radiation arrives across many wavelengths, most of which our eyes never notice. The sun is communicating with the solar system constantly, not with words, but with light, plasma, and fields. Some messages are steady and life-giving, some are stormy. Most pass unnoticed because Earth's atmosphere and magnetic field shelter us. We live beneath layers of protection, warmed by a star whose outer atmosphere is far more restless than the gentle patch of sun on a blanket suggests. The solar atmosphere is also a place where scale becomes slippery. A feature that looks small on an image of the sun may be larger than Earth. A loop that seems delicate may contain plasma guided across distances that dwarf our planet. A flare that appears as a bright flash may release energy beyond easy imagination. This is one of the challenges of solar science for the human mind. We can understand the ideas, but the sizes resist instinct. Our brains know rooms, roads, hills, storms, and cities. The sun works in scales where a small detail can swallow a planet. It is useful to remember this gently, not to feel insignificant, but to feel properly oriented. We are small, yes, but we are also capable of understanding a star, which is not a bad achievement for creatures who still sometimes lose their keys while holding them. There is a practical reason to care about the atmosphere above the sun, but there is also a deeper reason. The solar atmosphere is where the sun becomes connected to space. Below the photosphere, the energy is mostly hidden, slowly working outward through dense layers. At the surface and above it, that energy becomes visible, dynamic, and outward-reaching. The atmosphere is where internal motion meets space. It is where magnetism rises from below and opens into the solar system. It is where a star stops being only a source of light and becomes an active presence across vast distances. To study the solar atmosphere is to study the sun in conversation with its surroundings. As we follow this outward view, it becomes easier to appreciate why the sun cannot be treated as a simple object with a simple top. Above it is not one layer, but a changing sequence of regions. Each has its own behaviour, each is connected to the ones below. The photosphere shines, the chromosphere flickers and jets. The transition region climbs sharply in temperature. The corona glows faintly but burns hot in the language of particle motion. The solar wind escapes and keeps going. Magnetic fields tie these regions together, sometimes calmly, sometimes explosively. The whole atmosphere breathes outward into space, carrying the sun's influence far beyond what we can see. From Earth, we mostly receive the finished result as daylight. We feel warmth. We see blue sky. We notice shadows. We complain when it is too hot, then complain later when there is not enough sun, because humans are complicated weather critics. But above the sun, the processes behind that ordinary daylight continue with astonishing variety. The star is constantly shedding particles, reshaping fields, releasing energy, and forming structures that live and fade. It is not merely shining, it is active. This outward story naturally leads us back toward the question of what lies beneath the visible face. The atmosphere above the sun is shaped by energy and magnetism that do not begin there. They rise from deeper layers, from motions below the photosphere, from the churning plasma and the hidden workings of the solar interior. The corona may glow above, but its behaviour is rooted in what the sun is doing underneath. To understand the loops, flares, winds and strange heat of the outer atmosphere, we eventually have to descend beneath the surface that our eyes mistake for an edge. Beneath that bright face lies the interior, where pressure, fusion, radiation and convection build the light that finally escapes into the atmosphere above. Below the sun's bright face, there is no solid ground, no hidden floor, no glowing crust with some secret landscape tucked underneath it. There are no caves of fire, no tunnels, no buried chambers where sunlight is stored like treasure in a furnace. The sun is not built like Earth. It has no rocky shell, no mantle of minerals, no core of iron in the way our planet does. If you could somehow descend beneath the visible surface, protected from heat, radiation, pressure, and several other problems that would make the journey rather unpopular with travel agencies, you would not pass through a firm boundary. You would move into deeper and denser plasma, into layers where light struggles to escape, where matter behaves less like gas in a room and more like a compressed, glowing, electrically charged ocean under the weight of a star. From far away, the sun looks as though it has a surface, because visible light seems to come from a definite edge. But that edge is not a solid skin. It is the photosphere, the layer where the sun finally becomes transparent enough for photons to stream outward freely into space. Below it, the material is too dense and opaque. Light is constantly absorbed, scattered, redirected, and absorbed again. Above it, light can escape. So the surface we see is really a kind of visual horizon, the place where the interior stops hiding its light so thoroughly. It is not the bottom of the sky or the top of a solid body. It is the glowing threshold between the sun's hidden depths and the atmosphere above. To understand what lies below that visible face, it helps to set aside the picture of a flame. The sun is often described as burning, and in ordinary speech that is fine enough. We speak of the burning sun because it is hot and bright, and because language was built by people standing under daylight, not by plasma physicists with carefully labelled diagrams. But the sun is not burning like a candle, a log, or a campfire. Chemical burning requires fuel reacting with oxygen, and if the sun were powered that way, it would not have lasted nearly long enough for Earth's long story of oceans, continents, microbes, forests, animals, and eventually sleepy science channels. The sun shines because of nuclear fusion in its core. Deep inside, under immense pressure and temperature, hydrogen nuclei combine through a sequence of reactions that ultimately forms helium and releases energy. That energy works its way outward, layer by layer, until some of it becomes the sunlight that reaches Earth. The core is the deepest part of the sun, and it is where the story of sunlight begins. It occupies only the central region of the sun, but it is the engine that supports the whole star. Gravity pulls all the sun's material inward. The mass of the layers above presses down on the center with enormous weight. Under those conditions, the core becomes hot and dense enough for fusion to occur. Individual particles move so rapidly and are packed so closely that they can overcome barriers that would normally keep them apart. The result is a slow, steady production of energy that has kept the sun shining for billions of years. Slow and steady is important here. It might be tempting to imagine the sun's core as a raging explosion trapped inside a star. But stars like the sun are not giant bombs continually trying to burst apart in a wild panic. They are balanced systems. Gravity presses inward. Pressure from hot material and radiation pushes outward. The sun remains stable because these influences are in long-lasting balance. If the core produced too much energy, the inner regions would expand and cool slightly, reducing the rate of fusion. If the core produced too little, gravity would compress it more, heating it and increasing fusion. The sun has a kind of built-in self-regulation, not conscious of course, but governed by physics. It is a natural thermostat on a stellar scale, though one should not try adjusting it from the hallway. This balance is called hydrostatic equilibrium in scientific language, but we can understand it without formal terms. Imagine trying to hold up a heavy blanket with warm air underneath it. If the warm air is strong enough, the blanket lifts. If the weight is too much, it presses down. In the sun, the situation is vastly more complex, but the basic idea is inward pull, balanced by outward support. Every layer is held in place by this relationship. The sun does not collapse because the interior pushes outward. It does not fly apart because gravity holds it in. The visible calm of the sun, the dependable light that plants and people rely on, comes from this deep balance below the surface. The energy released in the core does not simply shoot straight out and arrive at the surface like a messenger taking a clear road through a quiet town. The sun's interior is far too dense for that. Photons created or re-emitted inside the sun are quickly absorbed or scattered by particles. They change direction again and again. Their outward journey is not a clean line, but a long, tangled wandering. A photon may travel only a short distance before interacting with matter, then be replaced by another photon moving in a new direction, then another and another. The energy moves outward, but in a slow and indirect way, like someone trying to leave a crowded theatre while being politely but constantly redirected by everyone else in the building. Above the core lies the radiative zone. In this region, energy is transported mainly by radiation, meaning it moves from particle to particle through repeated absorption and emission of light. The material is still extremely hot and dense, but fusion is no longer the main energy source there. Instead, the radiative zone is the great middle passage through which energy from the core slowly makes its way outward. This region is quiet in one sense compared with the churning layers above it, but quiet should not be mistaken for simple. It is a deep, opaque interior where light is trapped in a long random walk, where energy drifts outward over immense timescales. People often find it surprising that sunlight may take a very long time to emerge from the sun after the energy is first produced in the core. The exact journey is complicated because energy is constantly absorbed and re-emitted, so it is not usually useful to imagine one little photon patiently keeping a diary from the center to the surface. But the broader point is true. Energy generated deep inside the sun can take a very long time to work its way outward through the dense interior. Then, once it finally escapes from the photosphere, it crosses the space to Earth in only minutes. So the sunlight on your hand has a strange double history. Its final trip across space is quick. Its earlier passage through the sun may be ancient by human standards. A sunbeam can feel immediate and fresh, but the energy behind it began its outward journey in a hidden interior, where nothing like human time feels very relevant. Farther outward, the radiative zone gives way to the convective zone. Here, the method of energy transport changes. The material becomes less dense and more opaque, in a way that makes radiation alone less efficient at carrying energy. Instead, hot plasma rises, cools near the surface, and sinks again. This is convection, the same basic pattern you see in boiling water, although comparing the sun to a pot of soup is a little unfair to the soup. In the convective zone, enormous currents move energy upward through physical motion. Hot material from deeper regions rises toward the surface. After losing some energy, it becomes cooler and denser relative to its surroundings, and it sinks back down. This constant overturning gives the outer layers of the sun a restless, boiling character. Near the visible surface, convection creates the mottled pattern known as granulation. Through solar telescopes, the photosphere appears covered in bright cells with darker edges. Each bright center is hot material rising. Each darker boundary is cooler material sinking. These cells are not tiny in human terms. Many are comparable in size to regions on Earth. They appear, shift, and fade over minutes. The sun's surface is therefore not a smooth shining shell, but a constantly renewed pattern of rising and falling plasma. It is as though the star's hidden interior is pressing upward everywhere at once, bringing heat toward the surface in countless moving patches. There are larger patterns too. Supergranulation describes broader flows that cover larger regions and last longer. Beneath the surface, the sun's convective motions become complex, layered, and turbulent. The plasma does not behave like a neatly stirred pot. It is influenced by rotation, magnetism, density changes, temperature gradients, and the fact that the sun is a sphere made of electrically charged material. These motions help generate and shape the sun's magnetic field. The interior and atmosphere are deeply connected. The magnetic loops, sunspots, flares, and coronal structures above the surface are rooted in motions below it. This is where the hidden interior begins to explain the active atmosphere we visited before. The sun's magnetic field is produced by the motion of conducting plasma inside the star. Because plasma contains charged particles, its motion can create and sustain magnetic fields. The sun also rotates differentially, with different latitudes turning at different rates. The combination of internal flows and uneven rotation twists and stretches magnetic fields. Over time, these fields can rise toward the surface, forming active regions. Where strong magnetic fields emerge, convection can be suppressed, creating cooler patches that appear as sunspots. Those dark marks on the sun are not stains or holes, they are signs of magnetism rising from below. A sunspot looks dark only because it is cooler than the surrounding photosphere. It is still extremely hot and bright by earthly standards. If you could somehow place a sunspot alone in the night sky, separate from the brighter surface around it, it would glow brilliantly. But against the hotter surrounding photosphere, it appears darker. This is a useful reminder that brightness is always relative. A thing can be dazzling and still look dim beside something even more dazzling. The sun is very good at making comparisons difficult. Below a sunspot, magnetic fields interfere with the normal upward transport of heat. The plasma is constrained by the magnetic field, and convection is reduced. Heat still exists, of course, but the surface region cools compared with its surroundings. Sunspots often appear in pairs or groups, reflecting magnetic field lines emerging from one region and re-entering another. Around these areas, the solar atmosphere may become more active. Flares and eruptions often begin where magnetic fields are especially twisted or stressed. So the visible dark spots on the surface are like small clues written by the hidden interior, hints of magnetic structures rising from depths we cannot see directly. But how do we know what is inside the Sun if we cannot look beneath the photosphere in ordinary light? This is one of the most impressive achievements of solar science. Astronomers study the Sun's interior through several methods. One is theory, using the laws of physics to model how pressure, temperature, energy production, and transport should behave in a star of the Sun's mass and composition. Another is observation of the Sun's surface and output, checking whether models match what the Sun actually does. And one especially elegant method is heliosismology, the study of waves moving through the Sun. The Sun vibrates. It rings, not like a bell you could hear in air, but through pressure waves travelling inside it. These waves cause tiny motions at the surface, patterns that can be measured with sensitive instruments. By studying how the surface oscillates, scientists can infer conditions below, much as geologists study earthquakes to learn about Earth's interior. The Sun is filled with waves bouncing through its layers, affected by temperature, density, flow, and rotation. Heliosismology has allowed scientists to map aspects of the solar interior, including how different layers rotate. It is a beautiful idea. The hidden Sun reveals itself through trembling. These vibrations are not random noise, they carry information. Some waves travel deeper. Others remain closer to the surface. Their frequencies and patterns change depending on the structure they pass through. By analysing them carefully, scientists can build a picture of regions no spacecraft could survive and no camera could see. In this way, the Sun becomes something like a musical instrument, with its internal structure shaping the notes it can produce. We do not hear the sound directly in space, because space does not carry sound the way air does, but the motions can be translated into data, and the data can reveal the star's interior. The core, radiative zone, and convective zone are not separated by hard walls. These are regions defined by changing conditions and dominant processes. The Sun gradually changes from one kind of behaviour to another. The core is where fusion produces energy. The radiative zone is where energy moves mainly through radiation. The convective zone is where energy moves mainly through rising and sinking plasma. Near the boundary between the radiative and convective zones lies an important region often associated with the generation of the Sun's magnetic field. There, changes in rotation and flow may help stretch magnetic fields in ways that contribute to the solar cycle. It is one of the hidden places where the Sun's long rhythm of activity may be organised. The solar cycle itself is a surface and atmospheric phenomenon with deep roots. Over roughly 11 years, the number of sunspots rises and falls. Magnetic activity increases and decreases. The Sun moves from quieter periods to more active ones and back again. But beneath that visible cycle lies the internal motion of plasma and magnetic field. The Sun's hidden interior is not merely a furnace sending heat outward. It is a dynamic magnetic engine. The patterns we see above the surface are linked to flows and fields below it. The atmosphere may be where the drama becomes visible, but the stage machinery is deeper down. The interior also tells us why the Sun is stable for so long. In the core, fusion converts hydrogen to helium gradually. The Sun has a large supply of hydrogen, and the conditions in the core allow it to release energy at a rate that is enormous to us, but moderate for a star of its size. This is why the Sun can shine for billions of years. If fusion happened too quickly, the Sun's life would be short and violent. If it happened too slowly, the star might not shine as it does. The balance between gravity, pressure, temperature and fusion rate produces a long, steady main period of stellar life. Earth exists during that stable middle age, and life has depended on the Sun's patience. Even so, the Sun is slowly changing. As hydrogen is converted into helium in the core's composition evolves. Over very long times, the Sun gradually becomes brighter. This change is too slow to notice across a human lifetime, but it matters across geological time. The early Sun was somewhat dimmer than it is today, and Earth's climate history has been shaped by many interacting factors, including atmospheric composition, geological cycles, and solar evolution. In the far future, as the Sun continues to evolve, it will not remain as it is now. The hidden interior is the clock of the star's life, not a clock with hands and numbers, but a slow transformation written in nuclear fuel and gravitational balance. When the hydrogen in the core becomes depleted far in the future, the Sun's structure will change dramatically. Fusion will shift into surrounding regions, the outer layers will expand, the Sun will become a red giant. This is not part of our immediate story, and it is certainly not something to lose sleep over tonight. The timescales are far beyond human planning, beyond nations, beyond species, beyond the familiar categories of concern. But it reminds us that the interior is not static. It is evolving. A star's surface appearance at any moment is only a visible expression of a long internal life. The density inside the Sun increases as we go deeper. Near the surface, the plasma is thin compared with the interior. Deeper down, the weight of the material above compresses everything below. The core is extremely dense and hot, yet it is still plasma, not a solid object. We should be careful not to picture the core as a glowing metal ball. It's a region of intensely compressed ionized matter. The deeper we go, the more extreme the pressure becomes. Ordinary human experience offers no comfortable analogy. Even the deepest ocean trenches on Earth are gentle by comparison. The centre of the Sun is a place where matter is forced into conditions that can only be described through physics and imagination working together. The energy produced there eventually supports life here, which is one of the great connections in nature. A process in the Sun's core, hidden beneath hundreds of thousands of miles of plasma, leads eventually to light falling on a leaf. The leaf uses that light to build sugars. Those sugars feed ecosystems. Animals eat plants or eat other animals that ate plants. Ancient sunlight stored in living matter can become fuel, food, warmth, movement, and thought. Even the act of listening to a quiet explanation at night depends indirectly on the Sun's deep interior, because your body runs on energy that can be traced through life's pathways back towards solar light. The core of the Sun is not only an astronomical engine, it is part of the chain that makes forests, bread, weather, and wakeful minds possible. Below the Sun's surface, then, is not simply heat. There is structure. There is the core where fusion begins the flow of energy. There is the radiative zone where energy slowly diffuses outward. There is the convective zone where plasma rises and sinks in great currents. There are internal waves that allow us to study hidden layers. There are magnetic fields generated and shaped by motion. There are gradual changes that mark the Sun's long life. And there is an immense balance between gravity and pressure, a balance so successful that we experience it as ordinary daylight. It is worth pausing on that word ordinary. Daylight feels ordinary because it arrives so often, but ordinary does not mean simple. Morning light is the final outward expression of a star's interior physics. The brightness on a windowsill began with nuclear reactions deep in a core no eye can see. It travelled through dense plasma, through regions where radiation struggled and convection churned. It passed through the photosphere into space, crossed the gap between Sun and Earth, entered our atmosphere, scattered into blue sky, and finally landed on the world gently enough that we can read a book by it. There is a quiet miracle in the fact that something so extreme can arrive as something so soft. The hidden interior also protects us from a common misunderstanding. Because the Sun is hot and bright, it can seem as if its energy comes from the surface. After all, the surface is what shines. But the surface is only where the energy escapes. The source lies far below. This is true of many things in nature. What we see is often the outer expression of deeper processes. A wave on the ocean's surface is shaped by wind, gravity, depth, and motion below. A tree's leaves are supported by roots and internal circulation. A person's calm expression may sit above a great deal of unseen thought, though hopefully not too much if they are trying to fall asleep. The sun's visible face is the final layer of a hidden system. The contrast between surface and interior can be especially striking when we think about time. The photosphere changes in minutes as granules appear and disappear. Sunspots may last days or weeks. The magnetic cycle unfolds over years. Energy transport from the core outward occurs over much longer timescales. Stellar evolution takes billions of years. The sun contains many clocks at once. Its surface flickers with short-lived patterns. Its interior carries energy slowly. Its core changes across ages. When we look at the sun, we see one object, but it is layered not only in space but in time. This layered time helps explain why studying the sun requires patience and different kinds of instruments. To observe surface granulation, scientists use telescopes with high resolution and short exposures. To track sunspots and the solar cycle, they gather records across years. To understand the core, they use models, helioseismology, and particles called neutrinos that can escape from the core more directly than light. Neutrinos are produced in nuclear reactions and interact so weakly with matter that many pass straight through the sun and then through Earth, as if both were nearly transparent. Detecting them is difficult, but they provide direct evidence of fusion in the core. They are like tiny messengers from the hidden engine, almost unwilling to speak to anything, but valuable when they do. Neutrino observations were historically important because early measurements detected fewer solar neutrinos than expected. This puzzle eventually helped reveal that neutrinos can change type as they travel, a discovery with significance beyond solar physics. In that way, trying to understand the sun's interior led to deeper insight into particle physics. The sun is not only a subject of astronomy, it is a laboratory for fundamental physics, conveniently located nearby by cosmic standards, though still far enough away to discourage casual visits. The deeper we go in thought, the more the sun becomes a set of connected processes rather than a simple object. Fusion in the core produces energy and neutrinos. Radiation carries energy outward through dense layers. Convection carries it farther by motion. Surface flows shape granulation. Interior rotation and plasma motion generate magnetic fields. Magnetic fields rise and form sunspots. Active regions energize the atmosphere. The corona releases solar wind. The solar wind reaches Earth. Earth's magnetic field responds. Auroras glow. A person standing under those auroras may look up and see light in the sky that began with a chain of events linked back to the sun's hidden interior. This is not a poetic exaggeration. It is a physical connection, though it is also rather lovely. There is no need to imagine the sun as a perfectly understood machine. Many details remain under active study. Scientists continue to investigate the solar dynamo, the exact processes behind magnetic field generation, the transport of energy through different layers, the connection between interior flows and surface activity, and the way waves move through the sun. Better observations keep refining the picture. The sun is close, bright, and essential, but it is not simple. Familiarity does not mean mastery. In science, the nearest star still has secrets. For a sleepy mind, perhaps the gentlest way to hold all this is to imagine the visible sun as the glowing surface of a deep, moving sea. Beneath it, not water, but plasma. Not currents of cold and warm ocean, but currents of charged matter carrying energy. Not a rocky bottom, but a core where fusion steadily releases the power that supports the star. The surface shimmers with granules because material rises and falls below. Dark sunspots mark places where magnetism from within has changed the flow of heat. The atmosphere above glows and erupts because fields rooted below have risen and tangled. Nothing visible is separate from what is hidden. And so, below the sun is the source of its patience. The hidden interior is why the sun can shine day after day, with enough stability for life to build itself around the rhythm of light. It is why our planet has climates, seasons, photosynthesis, and warmth. It is why mornings happen with such reliability that we can forget how extraordinary they are. Beneath that bright disk is a layered star balanced between inward gravity and outward pressure, generating energy in its core and transporting it outward through deep regions of radiation and convection. As we move onward from the hidden interior, the next step is to connect what happens below with what rises above. The sun's depths do not merely produce light, they also help create magnetic fields that push through the visible surface and shape the atmosphere. These fields form loops, spots, arcs, eruptions, and storms. They are the invisible threads tying the inner sun to the outer sun, the below to the above, and they are where the next part of the journey begins. The sun's light is the part we notice first, but its magnetism is the part that makes it restless. Without magnetism, the sun would still be a star, still hot, still bright, still powered by fusion deep inside. But it would not have the same dark spots crossing its face, the same towering arcs of glowing plasma, the same sudden flares, the same enormous eruptions that send material racing into space. The magnetic field is the sun's hidden handwriting, written across its surface and atmosphere in loops, streaks, knots, and storms. It is invisible by itself, but it reveals its presence by guiding charged particles, shaping hot plasma, and storing energy until the sun, after a certain amount of internal patience, releases it with a force that makes earthly weather seem very well behaved. To understand these magnetic threads, we have to remember that the sun is not made of ordinary neutral gas in the way we might imagine air in a room. The sun is made mostly of plasma, a state of matter where many atoms have been stripped into charged particles. Electrons move separately from atomic nuclei. This matters because charged particles respond to electric and magnetic fields. They do not drift through magnetism as if nothing is there. They are guided by it, constrained by it, sometimes trapped along it, and sometimes flung by changes in it. In the sun, magnetism and plasma are deeply linked. The plasma moves and helps generate magnetic fields. The magnetic fields shape the plasma's motion in return. It is a relationship, a continuous exchange, like an invisible dance in which both partners keep changing the steps. This is very different from the way we meet magnetism in daily life. A small magnet on a refrigerator feels simple. It sticks or it does not. It holds up a shopping list, a child's drawing, or a reminder to buy something you will still forget once you are in the shop. The magnet seems solid, quiet, and dependable. Solar magnetism is not like that. It is stretched through a moving star. It is tangled by rotation. It is carried upward by rising plasma. It breaks through the surface, arches into the atmosphere, rearranges itself, and sometimes snaps into new shapes. A refrigerator magnet has a nice modest life. Solar magnetism has drama. The source of the sun's magnetic field lies in its moving interior. The sun rotates, but because it is not solid, different parts rotate at different speeds. Near the equator, the sun turns faster than it does near the poles. Beneath the surface, plasma circulates in complicated currents. Hot material rises, cooler material sinks, and large-scale flows move through the outer layers. Since plasma conducts electricity, these motions can generate and sustain magnetic fields. Scientists often describe this as a dynamo, a natural engine that converts motion into magnetism. It is not a machine with gears, belts, and a helpful instruction manual. It is a vast, turbulent, rotating, electrically conducting, star-building magnetic structure from its own motion. The uneven rotation of the sun is especially important. Imagine drawing a few straight lines from north to south on a softball, then twisting the middle faster than the top and bottom. The lines would stretch and wrap around. Something similar happens to the sun's magnetic field. Field lines that once had a simpler arrangement become wound around the star. They can be twisted, strengthened, and pulled into long bands beneath the surface. Over time, parts of these magnetic fields become buoyant and rise upward through the plasma. They do not rise like bubbles in water exactly, but the comparison gives the right gentle direction. Magnetic regions can push toward the surface, carrying with them the stored structure of the hidden interior. When a magnetic field emerges through the photosphere, it can create sunspots. These dark patches are among the oldest solar features humans have recorded, though observing them safely requires proper equipment. Sunspots look dark against the bright solar surface because they are cooler than their surroundings. They are still far hotter than anything we would call cold. A sunspot placed alone in space would shine brightly. But on the Sun, surrounded by hotter material, it appears dim. The reason it is cooler is that strong magnetic fields interfere with convection, the normal rising and sinking motion that brings heat toward the surface. Where magnetism becomes intense, it can reduce the upward flow of hot plasma, leaving the surface region cooler than nearby areas. Sunspots often appear in pairs or groups because magnetic fields emerge from the Sun in loops. One part of a field rises out of the surface, arches through the atmosphere and returns to the surface elsewhere. In simple terms, one region may act like one magnetic polarity and the other like the opposite polarity. The actual situation can be much more tangled, but the broad picture is useful. A sunspot group is not merely a collection of blemishes on a glowing face. It is a place where magnetic fields from the interior have pushed through the surface and connected the layers below to the atmosphere above. These magnetic loops can be enormous. Some rise high into the corona, the Sun's outer atmosphere, carrying plasma along their arches. In ultraviolet and X-ray images, they can glow as bright curves above active regions. They may look delicate in photographs, like fine threads or graceful bridges, but the scale is staggering. A loop that appears small on an image of the Sun may be large enough to dwarf Earth. The word thread feels gentle, almost domestic, as if the Sun were sewing its atmosphere together. In a way it is, but these threads are magnetic structures filled with plasma stretching across distances that make our usual sense of size quietly give up and sit down. The plasma in these loops does not simply hang there at random. Charge particles tend to move along magnetic field lines more easily than across them, so the field guides the material. That is why the loops become visible. The magnetic field itself cannot be seen directly by human eyes, but the plasma tracing it can glow in particular kinds of light. It is like seeing the shape of wind by watching leaves move, or noticing ocean currents by the drift of foam. The field is the structure, the glowing plasma is the clue. Some magnetic structures remain stable for a while. Others become unstable. The Sun is continually moving beneath them. Surface flows shift the bases of the magnetic loops. New magnetic regions emerge. Old ones decay. Field lines become twisted, stretched, braided, and pressed together. When magnetic fields with different directions are pushed into contact, they can suddenly rearrange. This process is called magnetic reconnection. It is one of the most important ideas in understanding solar activity. During reconnection, magnetic field lines change their connections, and stored magnetic energy is converted into heat, radiation, and particle motion. The effect can be sudden and powerful, like a tangled rubber band snapping into a simpler shape, except the rubber band is a magnetic field in a star, and the snap can affect planets. This is how solar flares can occur. In an active region, magnetic energy builds as fields twist and stress. Then, when reconnection happens, energy is released rapidly. The atmosphere brightens across many wavelengths. Radiation surges outward. Particles may be accelerated to high speeds. From Earth, a flare might be registered by instruments as a burst of X-rays or ultraviolet light. To the Sun, it is a local reorganization of magnetic energy. To us, it can be a space weather event. A strong flare can affect radio communication on Earth's sunlit side almost immediately. because electromagnetic radiation travels from the Sun to Earth in only minutes. The Sun's magnetic threads may rise and fall far away, but their effect can arrive at our planet very quickly. A flare is not always accompanied by a huge ejection of material, but often active magnetic regions can also launch coronal mass ejections. These are vast clouds of plasma and magnetic field thrown outward from the corona. When a magnetic structure above the Sun becomes unstable, it can lift away, dragging material with it. The eruption may look in solar images like a great bubble or cloud expanding into space. Again, the scale resists casual language. A coronal mass ejection can carry billions of tons of material. It can move at hundreds or even thousands of kilometers per second. If it is directed toward Earth, it may arrive after a period of travel through space and interact with our planet's magnetic field. Here the story becomes beautifully connected. The Sun's magnetic field rises from the interior, emerges at the surface, shapes loops in the atmosphere, releases energy through reconnection, and sometimes sends magnetized plasma outward into the solar system. Earth has its own magnetic field, generated by motion in its liquid outer core. When a solar eruption reaches Earth, the magnetic fields can interact. If conditions are right, energy enters Earth's magnetosphere and is guided toward the polar regions. Charged particles collide with gases high in the atmosphere, and the sky glows with auroras. The northern and southern lights are therefore not just pretty decorations near the poles. They are visible traces of magnetic conversation between Earth and Sun. It is rather touching, in a scientific sort of way, that the same kind of physical idea connects the deep interior of the Sun, the space between planets, and the glowing skies of Earth. Magnetism links places separated by enormous distances. It is invisible, but it makes itself known through motion and light. The aurora above a winter landscape may begin with magnetic stress in an active region on the Sun, with field lines twisting and reconnecting above a sunspot group. The event travels outward, reaches Earth, disturbs our magnetic shield, and paints the upper atmosphere. A person standing under that shimmering light might simply feel wonder. Behind the wonder is a chain of plasma physics stretching across space. The Sun's magnetic behaviour changes over a cycle of activity. Sunspots are not equally common all the time. During quieter periods, the Sun may show few spots. During more active periods, many spots appear, often in complex groups. This rise and fall follows a cycle of roughly 11 years, though the exact timing and strength vary. Over a longer magnetic cycle, the Sun's global magnetic field reverses polarity and then eventually returns. So the Sun has a rhythm, but not the simple tick of a clock. It's more like a natural pulse shaped by internal motion, rotation, and magnetism. At the beginning of a solar cycle, sunspots tend to appear at higher solar latitudes. As the cycle progresses, new spots appear closer to the equator. When scientists plot sunspot locations over time, the pattern resembles wings spreading and narrowing, sometimes called a butterfly diagram. It is a wonderfully gentle name for a record of a star's magnetic restlessness. The butterfly pattern shows that the Sun's magnetic field is organised in ways that change with time. It is not random speckling. It is a global magnetic process expressing itself through local dark regions. Sunspots can be simple or complex. A simple sunspot may have a dark central region and a lighter surrounding region with fine filamentary structure. Larger sunspot groups may contain many spots with mixed magnetic polarities. The more complex the magnetic arrangement, the greater the chance of strong flares. Scientists monitor active regions carefully, using magnetograms, which are maps showing magnetic fields on the solar surface. These maps reveal where magnetic polarity is positive or negative, where fields are concentrated, and where complex boundaries may store energy. To look at a magnetogram is to see the Sun in a different language. Not brightness, not colour, but magnetic pattern. The magnetic field also shapes prominences and filaments. A prominence is a huge structure of cooler, denser plasma suspended in the hot corona by magnetic fields. Seen at the edge of the sun, it may glow as a loop or curtain reaching outward into space. Seen against the bright disk, it appears as darker filament. These structures can last for days or longer, held in place by magnetic support. But if the magnetic configuration changes, a prominence can erupt, lifting away from the sun and sometimes contributing to a coronal mass ejection. Here again, the field acts like a scaffold, holding plasma in place until the scaffold changes. There is something almost architectural about the solar magnetic field. It builds arches, loops, arcades, and curtains. It supports material against gravity, it stores tension, it guides flow. But unlike human architecture, it is constantly remade. There are no permanent solar cathedrals of magnetism. A loop rises, glows, shifts, and fades. A sunspot appears, grows, fragments, and disappears. A prominence hangs like a glowing curtain, then lifts and escapes. The magnetic structures are grand but temporary. The sun does not keep its decorations for long. Because the sun is plasma, the magnetic field can be carried along with the moving material, a concept sometimes described as the field being frozen into the plasma. This does not mean frozen in the cold sense, which would be an ambitious misunderstanding near the sun. It means that under many solar conditions, the magnetic field tends to move with the plasma rather than slipping freely through it. As plasma flows, the field is dragged, stretched, and twisted. This is why the sun's surface motions matter so much. The churning photosphere is not merely a bright boundary. It is a moving base that tugs on magnetic structures extending into the atmosphere. These motions can send waves along magnetic field lines. Some of these waves may carry energy upward into the corona, helping explain why the corona is so hot. The sun's atmosphere is not heated only from below in the simple way a pan heats the air above it. Magnetic waves and reconnection likely play major roles. The surface motions shake the magnetic field. Energy travels upward. In the thin corona, that energy can be converted into heat. The exact balance of processes is still studied, but the connection between magnetism and coronal heating is central. The corona's surprising heat is not a random curiosity. It is tied to the restless magnetic threads rising from below. Solar magnetism also gives structure to the solar wind. In some regions, magnetic field lines loop back to the sun, trapping plasma. In other regions, field lines open outward, allowing material to escape more easily into space. Coronal holes, which appear darker in certain ultraviolet and X-ray images, are associated with open magnetic fields and faster solar wind streams. These streams flow outward and can influence Earth when our planet passes through them. So the configuration of the magnetic field above the sun affects the conditions experienced throughout the solar system. The field decides, in part, where plasma is held and where it is released. As the sun rotates, its magnetic field carried by the solar wind forms a spiral pattern through the solar system. This happens because the solar wind moves outward while the sun turns, somewhat like water spraying from a rotating garden sprinkler, though the actual physics is far richer and less likely to soak your shoes. The result is an interplanetary magnetic field that connects the planets to the sun in a broad, rotating structure. Earth is not simply orbiting in empty space. It is moving through a magnetized flow that began in the solar atmosphere. The magnetic threads also help explain why space weather is difficult to predict perfectly. Scientists can observe active regions, measure magnetic fields, detect eruptions, and model how events may travel through space. But the sun is complex. Small differences in magnetic structure can affect whether an eruption happens, how strong it is, where it goes, and how it interacts with Earth. Forecasting space weather is improving, but the sun does not hand out a neat schedule. It is more like trying to predict storms in an atmosphere made of plasma and magnetism, spread across millions of miles, with consequences travelling through interplanetary space. The challenge is large, but so is the motivation, because modern society depends on satellites, communication networks, electrical grids, aviation routes, and navigation systems that can all be affected by solar activity. Astronauts are especially vulnerable to solar particle events. Earth's atmosphere and magnetic field protect those of us on the ground from much of the sun's energetic behaviour. In space, protection is thinner and must be engineered. A strong solar event can increase radiation hazards beyond Earth's protective layers. Future missions to the Moon, Mars and beyond must account for the Sun's magnetic moods. The same star that makes life possible can also create dangerous conditions for travellers outside Earth's shield. This is not a contradiction. Nature is allowed to be generous and hazardous at the same time, which anyone who has admired the ocean from a safe distance may understand. The study of solar magnetism is therefore both beautiful and practical. It helps answer deep scientific questions about plasma, stars and magnetic fields. It also helps protect technology and people. Solar observatories watch the sun continuously, tracking spots, flares, eruptions, and the magnetic complexity of active regions. Spacecraft measure the solar wind and magnetic field near Earth, and sometimes closer to the sun. With each observation, scientists build a clearer picture of how the magnetic threads rise, twist, reconnect, and fall back or fly away. The falling part matters too. Not all plasma lifted by magnetic fields escapes. Much of it returns to the sun. In loops, material may flow upward along one side and downward along another. After flares, glowing arcs can form as plasma cools and settles. In prominences, material may drain back toward the surface if the magnetic support changes. The sun is constantly exchanging material between its lower atmosphere and corona. Some plasma escapes as solar wind or eruptions. Some rises and returns. The atmosphere is not a one-way fountain. It is a restless circulation shaped by gravity, pressure and magnetism. This rise and fall gives the sun a kind of breathing appearance in time-lapse images. Structures expand, contract, brighten, fade and collapse. Loops shimmer, filaments lift, jets shoot upward, arcs drain downward. The visible surface boils with convection, while the atmosphere above is traced by magnetic geometry. It is not random chaos, but neither is it simple order. It is organised restlessness, a phrase that suits the sun very well. The magnetic field provides structure, but the structure is always changing. There is a small lesson here about what invisible things can do. We cannot see magnetic fields directly, but they shape what we see. They make sunspots possible. They guide loops. They suspend prominences. They release flares. They launch eruptions. They direct solar wind. They connect the sun to Earth. Much of the most important action depends on something unseen. That is common in physics. Gravity cannot be seen directly either, only its effects. Air is invisible until dust or clouds reveal it. The structure of an atom is not seen by ordinary eyes, but it shapes matter. The sun's magnetic field is another invisible reality made visible through consequences. If you imagine the sun without magnetism, it becomes smoother, calmer, and less varied. But the real sun is not that simple. Its magnetic field is part of its personality, if one may use that word gently for a star. It gives the sun cycles and storms. It creates contrast on the surface. It lifts material into the corona. It sends disturbances through the solar system. It makes the sun not merely bright, but active. This activity is not a flaw in the star. It is a natural result of being a rotating, convecting ball of plasma. The magnetic threads that rise and fall are also part of the answer to our original question. What is above and below the sun really? Below the surface, motion generates and twists magnetic fields. At the surface, those fields emerge as spots and active regions. Above the surface, they form loops and structures in the atmosphere. Farther out, they are carried by the solar wind. The magnetic field is a bridge between below and above. It refuses to respect the neat boundary we imagine at the visible surface. It begins in hidden motion and reaches into space. This bridge is why a sunspot is not just a surface mark. It is the visible footpoint of deeper magnetism. It is why a coronal loop is not just an atmospheric ornament. It is tied to magnetic roots below. It is why auroras on Earth are not separate from the sun. They are part of a chain that begins with solar magnetic activity and ends with glowing gases in our upper atmosphere. The sun's magnetic threads connect layers, distances, and phenomena that might otherwise seem unrelated. For a moment, think of daylight again. Ordinary daylight contains no obvious sign of all this magnetic structure. A sunny morning can seem simple. The curtains brighten, the room warms, shadows form under chairs. Somewhere a cat chooses the best patch of light with an expertise that suggests cats have been conducting solar research privately for centuries. But on the sun itself, the source of that light is surrounded by magnetic motion. Beneath the calm warmth that reaches Earth is a star with loops taller than planets, spots wider than worlds, and invisible fields being twisted by plasma currents. The everyday and the cosmic sit together in the same beam of light. As we drift through this thought, it becomes clear that the sun is not only sending us light, it is sending a whole environment outward. Its magnetism shapes the corona. Its corona feeds the solar wind. Its solar wind flows through the solar system. And once we follow those magnetic threads far enough outward, we're no longer just above the surface of the sun. We're in interplanetary space, carried along by the stream of particles that leaves the star and moves past every planet. The next part of the journey follows that outward flow, away from the loops and spots, into the solar wind and the vast region of space that the sun quietly claims as its own. The magnetic threads rising from the sun do not stop at the edge of the corona. They do not simply arch upward, glow for a while, and then politely end where space begins. Some magnetic structures close back down to the solar surface, holding plasma in great loops and curtains. But other regions open outward, and from those open regions the sun continually releases a stream of charged particles into space. This stream is called the solar wind, and despite the familiar word wind, it is not like air moving across a field or a breeze coming through a window on a warm evening. It is a flow of plasma, thin but fast, carrying particles and magnetic fields away from the sun in all directions. It fills the solar system with the sun's presence. It brushes past planets, shapes magnetic environments, helps create auroras, and forms the vast bubble inside which Earth and its neighbouring worlds travel. It is easy to picture space as empty, because most of it is, by everyday standards, extraordinarily sparse. If you could scoop up a jar of interplanetary space, which is not recommended and would make for a disappointing souvenir, you would find almost nothing in it compared with the air around you. There are no breathable gases, no clouds, no ordinary weather, but empty does not mean inactive. Space around the sun contains sunlight, dust, magnetic fields, cosmic rays, and the solar wind. It is not a crowded room, but it is not nothing. It is a very thin, moving environment, and Earth is immersed in it every moment. The solar wind begins in the sun's outer atmosphere, especially in the corona. The corona is extremely hot and very thin. Its particles have so much energy that some of them can escape the sun's gravity and flow outward. This escaping plasma becomes the solar wind. The idea that the sun might have a continuous wind was not always obvious. From Earth, the space between planets seemed mostly empty, and the sun seemed to shine rather than blow. But observations of comet tails gave early clues that something from the sun was streaming outward. Comet tails often point away from the sun, not simply behind the comet's path, which suggests pressure from sunlight and particles flowing outward. Later measurements by spacecraft confirmed that a continuous solar wind moves through interplanetary space. The particles in the solar wind are mostly protons and electrons, along with some heavier ions. They are electrically charged, so they are strongly connected to magnetic fields. As the solar wind leaves the sun, it carries the sun's magnetic field outward with it. Because the sun rotates while the wind flows away, the magnetic field does not simply stretch straight out like spokes from a wheel. It becomes wound into a broad spiral structure across the solar system. A simple way to imagine it is a rotating sprinkler sending water outward, though in the real case the flow is plasma and magnetism rather than water, and the scale is large enough to make the sprinkler seem like a very small joke. The result is an interplanetary magnetic field that connects the space around the planets back to the sun. There are different kinds of solar wind. Some streams move faster and tend to come from coronal holes, regions where the sun's magnetic field is open to space. Other streams move more slowly and come from different parts of the corona. The fast wind and slow wind can interact as they travel outward. If a faster stream catches up with slower material ahead of it, the collision can create compressed regions that disturb the magnetic environment near planets. These interactions are part of space weather. They are not weather in the earthly sense of rain, clouds and windsocks having a meaningful afternoon. But they are changing conditions in space, driven mostly by the sun, and they matter for technology, and for any living beings who venture beyond Earth's protective layers. Earth is protected by its magnetic field. Our planet's magnetism forms a region around Earth called the magnetosphere, which deflects much of the solar wind. If Earth had no magnetic field, the solar wind would interact much more directly with the upper atmosphere. With the magnetosphere, many charged particles are guided around the planet rather than slamming straight into the atmosphere. The shape of this magnetic shield is not a perfect sphere. On the sunward side, it is compressed by the pressure of the solar wind. On the night side, it is stretched into a long tail extending away from the sun. Earth's magnetic environment is therefore shaped by the solar wind much as a windsock is shaped by moving air. Though again, the comparison becomes rather modest when the windsock is a planetary magnetic field, and the breeze is a stream of plasma from a star. This interaction between the solar wind and Earth's magnetic field is not always calm. When the solar wind carries certain magnetic orientations, or when a solar eruption arrives with a strong magnetic field of its own, energy can enter Earth's magnetosphere more efficiently. The magnetosphere becomes disturbed. Charged particles are accelerated and guided along magnetic field lines toward the polar regions. There they enter the upper atmosphere and collide with oxygen and nitrogen. Those collisions produce light. This is the aurora, the northern and southern lights, shimmering curtains and arcs that can glow green, red, purple, or blue, depending on the gases involved and the altitude of the emission. The aurora is often described as a sky display, but it is also the visible signature of Earth responding to the solar wind. There is something remarkable about the path from sun to aurora. The sun's corona releases plasma. That plasma travels outward as solar wind or as part of a larger eruption. It carries magnetic structure across space. It reaches Earth and presses against our magnetic shield. Energy is transferred into the magnetosphere. Particles move along field lines toward the poles. The atmosphere lights up. A person standing under an aurora may experience it as silence and beauty, but behind that beauty is a chain of physical events stretching from the sun's outer atmosphere to Earth's upper sky. The solar wind is the messenger, and the aurora is one of the ways the message becomes visible. Most of the time, the solar wind is not dangerous to life on Earth's surface, because the atmosphere and magnetic field provide strong protection. That protection is easy to forget because it is invisible. We do not wake up each morning and thank the magnetosphere, though perhaps it would not be the worst habit. Earth's atmosphere absorbs much harmful radiation, and the magnetic field helps deflect charged particles. Together they make the surface of our planet a relatively safe place beneath a sometimes stormy star. In orbit, however, the situation is different. Satellites, astronauts, and high-altitude systems can be affected by solar activity. A strong solar storm can increase radiation hazards, disturb satellite electronics, interfere with radio communication, alter the density of the upper atmosphere, and disrupt navigation signals. The upper atmosphere can swell when it's heated by increased solar radiation and particle activity. When that happens, satellites in low Earth orbit may experience more drag. They can lose altitude more quickly and may require adjustments. Navigation systems, which rely on precise timing and signals passing through the ionosphere, can become less accurate during geomagnetic disturbances. Power grids on the ground can also be affected when magnetic storms induce electrical currents in long conductors. These effects remind us that the solar wind is not merely an astronomy topic, it is part of the environmental background of modern civilization. Our technology reaches into space, and space is connected to the sun. The solar wind also shapes other planets differently depending on whether they have magnetic fields and atmospheres. Mercury, close to the Sun, has a weak magnetic field and a very thin exosphere. It is strongly exposed to solar particles and radiation. Venus has a thick atmosphere but no global magnetic field like Earth's, so the solar wind interacts directly with its upper atmosphere, forming an induced magnetic boundary. Mars also lacks a strong global magnetic field today, though it has remnants of ancient magnetism in parts of its crust. The solar wind interacts with the Martian atmosphere and has likely contributed to atmospheric loss over long timescales. Earth's magnetic field is not the only reason our atmosphere has endured, but it is an important part of our planet's relationship with the solar wind. Jupiter presents a very different case. It has an enormous magnetic field, the largest planetary magnetosphere in the solar system. The solar wind pushes against it, but Jupiter's own rotation, magnetic field, and volcanic moon Io create a vast and powerful magnetic environment. Saturn, Uranus, and Neptune also have magnetospheres shaped by both internal magnetic fields and the solar wind. Each planet responds differently. The solar wind is like a constant external influence, and each world answers according to its own magnetic and atmospheric character. Comets offer one of the most visible examples of the solar wind at work. When a comet approaches the inner solar system, sunlight heats its icy material, releasing gas and dust. The dust can form a curved tail influenced by the comet's motion and radiation pressure. The charged gas, however, is picked up by the solar wind and magnetic field, often forming a straighter ion tail pointing away from the sun. This is why comet tails do not simply trail behind like smoke from a moving train. They are sculpted by the sun's outward flow. A comet is a small icy body, but when it nears the sun it becomes a visible wind gauge for interplanetary space. The solar wind does not continue unchanged forever. As it flows outward, it expands and thins. It passes the orbits of the inner planets, then the outer planets, moving far beyond Neptune. Eventually it begins to slow as it encounters the interstellar medium, the thin gas, dust and magnetic fields between stars. The region dominated by the solar wind is called the heliosphere. This is the sun's great bubble of influence surrounding the solar system. The boundary is not a hard wall. It is a complex region where the outward flow from the sun meets material from the galaxy. The solar wind slows, becomes turbulent, and eventually gives way to interstellar conditions. This outer boundary is one answer to the question of how far the sun reaches. If we think of the sun only as the bright sphere in the sky, then it ends at the photosphere. If we include its atmosphere, it extends through the corona. If we include its wind and magnetic influence, it stretches far beyond the planets, forming the heliosphere. Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and countless smaller bodies all move inside this solar bubble. Even when night falls and the sun is hidden below the horizon, Earth remains inside the sun's extended environment. We are never really outside the sun's reach. The heliosphere helps shield the solar system from some cosmic rays, which are high-energy particles arriving from beyond the sun, often from powerful events elsewhere in the galaxy. The solar wind and its magnetic field can deflect or modulate some of these incoming particles. The degree of shielding changes with the solar cycle. When the sun is more active, its magnetic influence can reduce the number of some cosmic rays reaching the inner solar system. When solar activity is lower, more may get through. So the sun not only sends material outward, it also helps shape what enters from beyond. The solar system is not an isolated bubble, but it has a kind of moving boundary and a changing level of protection. A few spacecraft have travelled far enough to explore the outer reaches of the heliosphere. They have measured changes in particles and magnetic fields as they crossed from the sun-dominated environment into interstellar space. These journeys are among the most profound achievements of human exploration. A small machine built on Earth, launched from a planet warmed by the sun, travelled outward past the giant planets and eventually reached the region where the solar wind gives way to the galaxy. It is difficult to imagine a better demonstration that our local star is both home and gateway. We live in its light, and our machines have begun to cross the edge of its influence. Closer to the sun, other spacecraft study the solar wind near its source. By travelling into the inner solar system, they measure particles, fields, waves, and structures before they have been smoothed out by distance. These missions help scientists understand how the solar wind accelerates, how the corona releases material, and how magnetic fields behave near the sun. The closer we look, the more complex the solar wind becomes. It is not a simple, steady stream. It contains gusts, waves, turbulence, sudden bends in magnetic field direction, and structures linked to the sun's surface and atmosphere. Even the wind from a star has texture. The solar wind is sometimes described as a continuous outflow, which is true, but that phrase can make it sound too uniform. A river flows continuously too, but anyone who has watched a river knows it has ripples, eddies, currents, shallows, and sudden changes around rocks. The solar wind has its own versions of texture and disturbance. Fast streams, slow streams, shock waves, magnetic clouds, and turbulent regions move through interplanetary space. Earth's experience of the solar wind changes as the sun rotates and as active regions face toward or away from us. Space weather has patterns, but it also has surprises. The sun's rotation creates a repeating aspect to some solar wind conditions. If a coronal hole persists for more than one solar rotation, Earth may encounter a fast stream from it again when the sun turns that region back into view. This can produce recurring geomagnetic activity. Other events are more sudden, especially eruptions from active regions. A coronal mass ejection can be launched with little warning compared with the long distances involved, and its impact depends not only on whether it reaches Earth, but also on the orientation of its magnetic field. A glancing blow may cause mild disturbance. A direct impact with favourable magnetic orientation can produce a stronger storm. Space weather forecasting is therefore a mixture of observation, modelling, and humility. On Earth, the solar wind is mostly experienced indirectly. We do not feel it on our faces. It does not rustle leaves or move clouds. The ordinary wind you feel outside is caused by atmospheric pressure differences, driven largely by solar heating, but it is not the solar wind itself. The solar wind passes far above, in the realm of magnetospheres and upper atmospheres. Yet its effects can enter our lives through technology. A radio blackout, a navigation error, a satellite anomaly, a brilliant aurora seen unusually far south or north. These can be signs of the sun's distant activity reaching our planet. The solar wind is silent at the surface, but not irrelevant. There is a quiet irony in the fact that the sun gives us both stable daylight and unstable space weather. The same star that supports climate and photosynthesis also sends charged particles and magnetic disturbances outward. The same solar activity that creates beautiful auroras can challenge power systems and satellites. Nature rarely divides itself neatly into helpful and harmful. It acts according to physical processes, and life learns to live within them. Earth has done this for billions of years, protected by atmosphere, magnetism, distance, and a great deal of fortunate history. The solar wind also matters for the long-term evolution of atmospheres. Over geological time, Interactions between stellar wind and planetary atmospheres can influence how much gas a planet retains, especially if the planet lacks a strong magnetic field or has low gravity. Around other stars, stellar winds can be much stronger, especially for young active stars. Exoplanets orbiting close to their stars may face intense particle flows and radiation. Understanding our solar wind helps scientists think about habitability elsewhere. A planet's atmosphere does not exist in isolation. It exists in the environment created by its star. Young stars can be far more active than the Sun is today. The early Sun likely had stronger magnetic activity and a more intense wind. Earth's early atmosphere and magnetic field had to develop under those conditions. Mars, smaller and less able to hold onto an atmosphere, lost much of its early air over time. Venus took a different path, with a thick atmosphere and extreme greenhouse conditions. These worlds remind us that sunlight alone does not determine a planet's fate. Stellar wind, magnetic fields, gravity, chemistry, geology, and distance all play roles. The space around a planet is part of its environment, even if it looks empty. The term space around us can mean the region just above Earth, where satellites orbit and auroras glow. It can also mean the space between planets, filled by the solar wind. It can mean the heliosphere, the vast domain carved out by the Sun in the galaxy. All of these regions are connected. A flare above a sunspot can affect Earth's ionosphere. A coronal hole can send a fast stream that disturbs the magnetosphere. A coronal mass ejection can travel outward past Mars and beyond. The solar wind carries the Sun's influence into the spaces we once imagined as empty gaps between worlds. This changes how we picture the solar system. Instead of planets moving through a blank void around a central light, we can imagine planets embedded in a flowing medium, thin but meaningful. The Sun shines, yes, but it also streams. Its magnetic field extends outward. Its particles move past the planets. Its activity rises and falls. The solar system becomes less like a set of marbles around a lamp, and more like a set of worlds moving inside a vast, transparent, magnetized atmosphere. The word atmosphere is not perfect once we are far from the Sun, but the idea helps. The Sun creates an environment, and we live within it. The solar wind is not visible to human eyes, but we can detect it with instruments. Spacecraft measure particle speed, density, temperature, and magnetic field direction. They record shocks, waves, and turbulence. Observatories watch the Sun for eruptions that may send disturbances outward. Ground-based systems monitor geomagnetic activity. Together, these measurements form a picture of the invisible weather around our planet. It is a modern kind of skywatching. Ancient people watched clouds and stars. Today we also watch plasma and magnetism, and yet the ancient instinct remains. We look upward because what happens above us matters. Weather mattered to farmers and sailors. The sun mattered to calendars and seasons. Auroras inspired stories long before they were understood as charged particles in a magnetic field. Now we know that some of the sky's most mysterious lights are connected to the solar wind. Scientific explanation does not remove the wonder. If anything, it expands it. An aurora is beautiful as light. It is also beautiful as evidence that Earth is magnetically connected to a star. There is also a scale of intimacy here that can be easy to miss. The solar wind begins at the Sun, but its effects can touch Earth's atmosphere. It begins as escaping plasma, but it can influence the signals that guide your phone, the safety planning for astronauts, and the glow of polar skies. It is vast and thin, distant and practical. It is part of the background condition of our technological age, and part of the natural theatre of the planet. The Sun is not merely far away, it is actively present in the space around us. At the same time, the solar wind reminds us how protected the surface of Earth is. Down here, under the thick lower atmosphere, the Sun feels mostly like warmth and light. The more dangerous particles and radiation are filtered, deflected, absorbed, or redirected. We live in a sheltered layer, a calm room inside a much more energetic house. This should not make us fearful. It should make us appreciative. Earth is not protected by one single wall, but by overlapping systems. Distance reduces intensity. The magnetic field deflects charged particles. The atmosphere absorbs radiation and slows incoming material. Life evolved inside these protections and has learned to use the sun's gentler gifts. The space around the moon is different. The moon has no global magnetic shield and almost no atmosphere, so the solar wind reaches its surface directly. Particles from the sun strike lunar soil, gradually altering it over time. The moon's surface records space weather, in a way Earth's protected surface does not. Future lunar explorers will need to account for solar storms more directly. The same is true for journeys to Mars. Between planets, astronauts would travel through the solar wind, protected only by their spacecraft and mission planning. Understanding the sun's outflow is therefore essential for exploring beyond Earth. The solar wind also creates a faint but constant pressure. It is not strong enough to push planets around in any dramatic way, but it can affect small dust particles and the tails of comets. Along with sunlight itself, it helps shape the behavior of tiny material in the solar system. Dust, plasma, and magnetic fields interact in subtle ways. The solar system is full of small particles that respond to forces too delicate for us to notice in daily life, but important over long periods and great distances. At the larger scale, the heliosphere moves with the sun through the local interstellar medium. The sun is travelling through the galaxy, and its solar wind carves out a bubble as it goes. The shape of that bubble depends on the pressure of the solar wind, the surrounding interstellar material, and magnetic fields beyond the solar system. Scientists once often pictured the heliosphere as having a long comet-like tail trailing behind the sun's motion. But newer models suggest the structure may be more complex. The exact shape is still studied. This is a useful reminder that even the boundary of our solar home is not fully known. We are still mapping the edges of the sun's reach. The word reach is important. The sun reaches us with light in minutes. It reaches us with gravity continuously, holding Earth in orbit. It reaches us with particles and magnetic fields through the solar wind. It reaches into the outer solar system through the heliosphere. Different influences travel and act in different ways, but together they define the sun's domain. When we ask what surrounds us in space, the answer is not merely darkness. It is the extended presence of our star. This extended presence has rhythms. The solar cycle changes the sun's magnetic activity. The rotation of the sun brings active regions in and out of view. Eruptions send disturbances outward. Coronal holes produce recurring fast streams. Cosmic ray levels vary with solar activity. Auroras brighten and fade with geomagnetic conditions. The space around Earth is therefore constantly responding to changes at the sun. It is dynamic, but much of that dynamism is invisible unless instruments reveal it or auroras make it glow. Perhaps this is why the solar wind is such a good subject for a quiet science journey. It asks us to notice what is present even when unseen. It asks us to imagine a wind that does not move trees, a weather system without clouds, a boundary without walls, a connection between a star and a planet written in magnetism. It also asks us to see Earth not as separate from space, but as embedded in it. Our atmosphere is not the end of the story. Above it lies the magnetosphere. Beyond that lies the solar wind. Beyond that, the heliosphere. Beyond that, interstellar space. Each layer changes the meaning of around us. If you are listening at night, the sun may be hidden by Earth itself. Your part of the planet is turned away, resting in shadow. But the solar wind does not switch off. The sun's particles still stream outward. Earth's magnetic tail stretches away from the sun on the night side. Charged particles still move through near-Earth space. The star below your horizon remains active, and your planet remains inside its invisible flow. Night is not absence from the sun. It is simply Earth's way of giving your eyes a softer view, and if it is daytime where you are, the sunlight may make the sun seem direct and simple. Brightness comes down, shadows point away, the sky glows blue, but above that blue sky, far beyond the air, Earth's magnetic field is meeting the solar wind. The sun is not only illuminating your world, it is flowing around it. Every day, Earth sails through that stream, protected, shaped, and occasionally disturbed by it. The solar wind is part of the weather of space, and space is closer than it feels. Following that wind outward also prepares us to widen the view again. The sun's atmosphere becomes the solar wind. The solar wind fills the heliosphere. The heliosphere moves through the galaxy, and the sun itself, carrying all of this with it, is one star among many in the Milky Way. To understand what is above and below the sun, we eventually have to look beyond its own atmosphere and wind to the larger neighbourhood it travels through. The sun has a place in the galaxy, a path among other stars, and a relationship with the vast structure surrounding it. The wind tells us how far the sun reaches, but the galaxy tells us where the sun belongs. The solar wind tells us that the sun is not just a bright object with planets circling nearby. It creates a whole region around itself, a vast bubble moving through space. But even that bubble is not the end of the story, because the sun is also part of something much larger. It belongs to the Milky Way, a great spiral galaxy filled with stars, gas, dust, magnetic fields, dark matter, and long histories of birth, motion, collision, and change. The sun is our star, the centre of our daily sky, and the anchor of our planet's orbit. But in the galaxy it is one star among an immense crowd. It is neither at the centre nor at the edge. It is not the biggest, the brightest, the youngest, or the oldest. It is, in many ways, a fairly ordinary star in a fairly ordinary region. And yet, from this ordinary place came oceans, forests, insects, clouds, sleep, memory, and the strange ability of small creatures on a small planet to wonder where their star is going. The Milky Way appears from Earth as a pale band across the night sky, if you're lucky enough to stand somewhere dark enough to see it. In many cities, artificial light washes it away, and the galaxy that holds us becomes invisible behind street lamps, headlights, windows, signs, and the general human enthusiasm for making night less night-like. But under a dark sky, the Milky Way stretches overhead like a misty river. That glow is not a cloud in the atmosphere. It is the combined light of countless distant stars, too many and too faint for the eye to separate individually. When you see it, you are looking sideways through the disk of our own galaxy. We are inside it, so we do not see the Milky Way from the outside as a full spiral. We see it from within, like a firefly trying to understand the shape of the forest by looking between the trees. For a long time, humans did not know what the Milky Way really was. It was myth, path, river, spilled milk, road of souls, smoke, dust, a celestial feature woven into stories. Only with telescopes did it become clear that the pale band was made of stars. Later still, astronomers discovered that the Milky Way is only one galaxy among many, and that some of the faint smudges in the sky are not small clouds inside our own system, but entire galaxies of their own, vast islands of stars separated by enormous distances. This shift was one of the great expansions of human perspective. The sun went from being the centre of the universe in old models to being the centre of our planetary system, to being one star inside one galaxy among many. It is a humbling sequence, though the sun itself did not become any less important to us. Your home does not stop being your home just because there are other houses in other cities. The sun sits in the disk of the Milky Way, far from the galactic centre. The galaxy has a central bulge packed with older stars and, at its heart, a supermassive black hole. Around that central region spreads a broad disk, containing spiral arms, gas clouds, dust lanes, star-forming regions, and stars of many ages. The sun is located in a smaller spiral feature often called the Orion Arm or Orion Spur, between larger spiral arms. This is our local neighbourhood in the galaxy, though local is a generous word here. Galactic neighbourhoods are not the kind where you can borrow sugar, unless your neighbour happens to live several light years away and has a very patient delivery service. The Sun's distance from the galactic centre places it in a relatively calm region, compared with the crowded inner galaxy. Near the centre, stars are packed more densely, and gravitational interactions can be more intense. There is more radiation, more activity, more crowding, and more opportunity for close encounters. Out where the Sun resides, the stellar density is lower. Stars are separated by large distances. The nearest star system to the Sun is still so far away that light itself takes years to cross the gap. This spaciousness matters. It gives the solar system a relatively stable environment, with fewer close stellar encounters than might occur in denser regions. A quiet neighbourhood is not the only requirement for life, but it certainly does not hurt. Complex life has enough to worry about without nearby stars wandering through and rearranging the furniture. The Sun orbits the centre of the Milky Way. It does not sit motionless while the galaxy rotates around it. Just as Earth orbits the Sun follows a path around the galactic centre, carrying the entire solar system along. This orbit takes hundreds of millions of years to complete. That span is sometimes called a galactic year, though it is not a year in any earthly sense. One galactic year is longer than the time since dinosaurs first appeared and vanished, longer than the rise of mammals, longer than the entire written history of humanity many times over. The Sun has completed only a modest number of these galactic circuits since it formed. Our star is middle-aged, yet in terms of its journey around the Milky Way, it has only gone around the galaxy a few dozen times. It is an old traveller by human standards, but not a seasoned commuter by cosmic ones. As the Sun moves around the galaxy, it does not travel alone. The planets, moons, asteroids, comets, dust and spacecraft remain bound to it by gravity. The whole solar system moves together. It is easy to imagine Earth as circling a fixed sun, but the fuller picture is that Earth orbits a moving star, and that moving star orbits the galaxy. The solar system is therefore not a flat diagram pinned to empty space. It is a mobile structure, a gravitational family travelling through the Milky Way. The planets keep their orbits around the Sun because the Sun's gravity dominates their local motion, even while the galaxy's gravity guides the Sun along its larger path. The Sun's path through the galaxy is not a perfect circle drawn neatly on a classroom board. It is shaped by the distribution of mass in the Milky Way, including visible matter and dark matter. The galaxy is not simply a collection of stars in empty space. It has gas and dust, and it appears to be embedded in a much larger halo of dark matter, a form of matter that does not emit light but reveals its presence through gravity. The Sun's motion responds to this broad gravitational field. It moves around the galaxy, and over long times it also drifts slightly above and below the plane of the galactic disk. So even in the galaxy, above and below return as relative ideas. The Sun can move north and south of the galactic plane, crossing through the mid-plane over immense spans of time. This vertical motion is slow and broad, not a bobbing like a cork in water, but a gentle galactic oscillation. The plane of the Milky Way is where much of the galaxy's gas, dust and star formation are concentrated. The Sun's orbit keeps it near this disk, but not fixed perfectly within it. As it moves, it passes through regions of different density and structure. The interstellar medium around the Sun is very thin but not empty. It contains gas, dust, magnetic fields and cosmic rays. The heliosphere, the bubble created by the solar wind, moves through this interstellar material. The conditions around the heliosphere can change over long times as the Sun travels through different local clouds or regions. The space outside the solar bubble is not uniform. It is a subtle galactic environment, and our solar system passes through it like a ship moving through changing currents, too faint for the passengers to feel directly. The Sun's place in the galaxy may have mattered for the history of Earth. Scientists sometimes discuss the idea of a galactic habitable zone, a region in a galaxy where conditions may be more favourable for long-term planetary habitability. Too close to the galactic centre, the environment may be more crowded and energetic, with more frequent supernovae or disruptive gravitational encounters. Too far out, there may be fewer heavy elements needed to build rocky planets and complex chemistry, because those elements are created by earlier generations of stars and distributed through the galaxy over time. The Sun lies in a region where heavy elements are available, but the environment is not excessively crowded. This does not mean the Sun's location is magically perfect or uniquely chosen. It means that habitability depends not only on the distance between a planet and its star, but also on the larger galactic setting in which the star formed and lives. The Sun formed about 4.5 billion years ago from a cloud of gas and dust, enriched by earlier generations of stars. Those earlier stars made heavier elements through nuclear fusion and explosive events, then returned material to space. The cloud that became the Sun and planets contained hydrogen and helium, but also carbon, oxygen, silicon, iron, and other elements needed for rocky worlds and living chemistry. Earth is possible because the Sun was not among the first stars. It was born after the galaxy had already had time to process matter through stellar lives and deaths. In a very real sense, the Sun is a child of the galaxy's earlier history. So are we. The calcium in bones, the iron in blood, the oxygen we breathe, the silicon in rocks, all of it belongs to a long galactic recycling process. The Sun's place in the galaxy is not only a location, it is an inheritance. The birth environment of the Sun is not known in every detail, but it likely formed in a cluster or association with other young stars. Stars often form together inside large molecular clouds, where gravity pulls dense regions inward and new stars ignite. Over time, the cluster disperses. The Sun's original sibling stars have likely drifted away around the galaxy, mixed into the broader stellar population. Somewhere in the Milky Way, other stars may have formed from the same cloud as the Sun, sharing a chemical family resemblance. We do not know them by name, and they do not gather for reunions, though if they did, the catering would be difficult. The Sun today appears mostly solitary, but its origin was probably social, born among many stars before the galaxy's motions scattered the family. This matters because the early environment of a star can influence its planetary system. Nearby massive stars may flood a young system with radiation. Close stellar encounters can disturb disks of gas and dust. Supernovae nearby can inject radioactive materials or shock waves. The Sun's birth cluster may have played a role in shaping the early solar system, but it did not prevent stable planets from forming. After the Sun emerged from its natal cloud, a disk of leftover material around it became the source of planets, moons, asteroids, and comets. The galaxy provided the raw materials, gravity organized them, and the Sun became the central star of a new system. The Milky Way is not only the Sun's birthplace and path, it is also the night sky's background. When you look at constellations, you are seeing nearby stars within our galaxy. Some are much hotter than the Sun, some are cooler, some are giants, some are dwarfs, some are young and blue, some are old and red. The Sun is a yellowish main sequence star, meaning it is in the long, stable phase of fusing hydrogen in its core. In the enormous variety of stars, the Sun is neither extreme nor rare in the broadest sense, but its exact combination of mass, age, composition, stability, and planetary system is special to us because it allowed Earth's history to unfold as it did. A star does not have to be exceptional to be precious. Nearby stars move relative to the Sun. The stellar neighbourhood changes over time. The stars that are nearest today were not always nearest, and they will not remain so. Over tens of thousands, millions and billions of years, stars drift in their galactic orbits, passing at great distances from one another. Occasionally a star may pass relatively close by astronomical standards, perhaps disturbing the outer cloud of comets surrounding the solar system. Such encounters are rare but possible over the Sun's long life. The solar system is stable, but it is not sealed away from the galaxy. Gravity from passing stars, tides from the galaxy, and the broader interstellar environment can all influence the outermost regions over long timescales. One distant region that may be affected by the galaxy is the Oort cloud, a hypothetical vast shell of icy bodies far beyond the planets. It is thought to be the source of many long-period comets. These icy bodies are so far from the Sun that they are only loosely held by its gravity. Passing stars and galactic tides can nudge some of them inward, sending comets into the inner solar system after long ages in the cold dark. When a comet appears near the Sun, glowing and developing tails, it may be a visitor from this distant reservoir, stirred by the gravitational environment of the galaxy. In that way, even a comet in our sky may carry the faint signature of the Sun's place among other stars. The Sun's galactic motion also gives us a different way to think about time. We measure human time in seconds, days, years, and lifetimes. Earth measures its orbit around the Sun in years. The Sun measures its orbit around the galaxy in hundreds of millions of years. Geological changes on Earth, the rise and fall of species, the assembly and breakup of continents, the oxygenation of the atmosphere, the appearance of forests, the age of dinosaurs, the development of humans. All of these are tiny patterns inside the Sun's longer galactic journey. If the Sun could keep a travel diary, one orbit around the Milky Way would contain entire chapters of Earth's biological history. Fortunately for all of us, the Sun does not write diaries, which saves us from several 100 million years of entries beginning with still moving, still hot. The galactic centre itself is far away from us, hidden in visible light by dust, but observable in other wavelengths. At the centre lies a supermassive black hole, surrounded by stars moving in tight, fast orbits. This central object does not pull the Sun inward like a cosmic drain. That is a common misunderstanding about black holes and galaxies. The Sun orbits the galactic centre because of the gravity of the galaxy as a whole, not because it is being directly sucked toward a hole. The black hole is massive, but the galaxy contains far more mass spread throughout its stars, gas, dust, and dark matter. The Sun's orbit is governed by the overall gravitational structure, much as Earth's path around the Sun is governed by the Sun's gravity, but on a vastly larger and more distributed scale. The Milky Way itself is not motionless. It rotates. It moves through space within a group of nearby galaxies. It is on a long-term path that will eventually bring it into a major interaction with the Andromeda Galaxy, though that event lies far in the future. When galaxies interact, stars usually do not collide directly because the distances between them are so vast. Instead, gravity reshapes the galaxies, stretching streams of stars, triggering star formation, and eventually forming a new combined structure. The Sun may or may not still be in the same stage of its life by the time the Milky Way and Andromeda fully merge, depending on the details of timing and stellar evolution. Again, this belongs to deep future time, far beyond everyday concern. But it places the Sun inside an even larger cosmic motion. Our star orbits a galaxy that is itself part of a moving, evolving cosmic neighbourhood. It is easy to feel small in this picture, but smallness is not the same as meaninglessness. The Sun is small compared with the galaxy, and Earth is small compared with the Sun, and a person is small compared with Earth. Yet meaning does not scale simply with size. A galaxy cannot appreciate a sunrise. A nebula does not write music about winter light. A spiral arm does not wonder what lies above and below the Sun. These are things small minds do, and the fact that small minds can ask large questions is one of the more interesting features of the universe. The Sun's place in the galaxy tells us we are not central in a geometric sense, but it does not make our perspective empty. It makes it local, and local perspectives are where experience happens. The Sun's location also affects what we can see. Because we are inside the Milky Way's disk, dust blocks our view in some directions, especially toward the galactic centre in visible light. Radio, infrared, and other forms of observation help astronomers see through or around that dust. Our map of the galaxy has been built from careful measurement, including distances to stars, motion of gas, star clusters, variable stars, and more recently precise surveys of stellar positions and motions. Mapping the Milky Way from within is difficult. It is like trying to map an entire city while standing in one neighbourhood on a foggy night, with most of the roads hidden behind buildings and all the buildings slowly moving. Astronomers have done remarkably well under the circumstances. The sun helps define our local standard of observation, but it also complicates things. From Earth, we see stars from a moving platform. Earth orbits the sun, and the sun moves through the galaxy. Astronomers use these motions to measure distances and velocities, but they must also correct for them. The motion of nearby stars across the sky, called proper motion, reveals that the sky is not fixed. Constellations change shape over long times. The familiar patterns are temporary arrangements from our viewpoint. The stars of a constellation may not be physically close to one another. They only appear grouped because of our line of sight. As the sun and other stars move, the sky slowly rearranges itself. The night sky is not permanent. It only seems so because human lives are short compared with stellar motion. Our solar system also has an orientation within the galaxy. The plane in which the planets orbit the sun is tilted relative to the plane of the Milky Way. This means the solar system is not lying flat like a coin on the galactic disk. It is set at an angle. When people ask what is above or below the sun, this becomes another reminder that direction depends on the frame you choose. Above the sun relative to its north pole is not the same as above the galaxy's disk. Above Earth's horizon is different again. Space does not come with labels taped to it saying this way up. We bring directions from our own motion, gravity, and chosen reference points. The sun's motion through the local interstellar medium also creates a direction of travel, sometimes described in relation to the solar apex, the direction toward which the sun moves relative to nearby stars. This is another kind of above or ahead, not universal, but meaningful in a local sense. The heliosphere is shaped partly by this motion through surrounding material. The sun is like a moving source of wind travelling through a very thin galactic atmosphere. Its own wind pushes outward, while the interstellar medium presses back. The boundary between them depends on both. The solar system therefore has a kind of forward environment and trailing environment, though not as simple as a car moving through air. Plasma and magnetic fields make everything more complicated, as they often do, perhaps because the universe enjoys keeping scientists employed. The local interstellar medium around the sun is not uniform. It consists of clouds and regions with different densities, temperatures, and ionization states. The sun currently moves through a relatively low-density region, and its immediate surroundings are part of a local cloud within a larger area shaped by past stellar activity. Supernova and stellar winds from earlier generations can carve bubbles and structures in interstellar gas, so the sun's current neighbourhood is the result of a long history of stellar events. Even the apparent emptiness between stars has a biography. It has been heated, stirred, compressed, cleared, enriched, and shaped by stars that lived and died long before our present sky. The sun's chemical composition also reflects the galaxy's history. It contains mostly hydrogen and helium, like other stars, but also a small fraction of heavier elements. Astronomers call these heavier elements metals, which can be confusing because they include things like oxygen and carbon that people do not usually think of as metals while making breakfast. The amount of these heavier elements affects star and planet formation. A young disk with enough heavy material can form rocky planets, metallic cores, silicate mantles, icy bodies, and the chemical ingredients needed for life. The sun's composition tells us that it formed after the Milky Way had already been enriched by many earlier stars. We're not at the beginning of the galaxy's story. We're in a later chapter, made possible by what came before. There are stars older than the sun in the Milky Way, especially in the halo and globular clusters where ancient populations preserve clues from the early galaxy. There are also stars younger than the Sun forming today in cold molecular clouds. In star-forming regions, gravity gathers gas into dense knots, young stars ignite, and their radiation begins shaping the surrounding cloud. The galaxy continues to make stars, though not at the same pace throughout its history. The Sun belongs to one generation among many. It is old enough for its planets to have developed long histories, but not so old that it has left its stable main phase. For life on Earth, that timing has been crucial. A star that changes too quickly gives life less time. A star that is too violent may be difficult for atmospheres and biology. The Sun's long stability has been one of Earth's quiet blessings. The Sun is sometimes described as a fairly typical star, but that phrase needs care. Many stars in the galaxy are smaller, cooler red dwarfs. In that sense, the Sun is more massive and brighter than the most common stars. But among stars visible to the naked eye, it would seem modest, because the stars we easily see across great distances tend to be intrinsically bright. The Sun would not be an impressive naked eye star if viewed from far away. It would fade into the background of the Milky Way. From another planetary system, our Sun might be just one ordinary point of light, perhaps unnoticed unless someone there had very good telescopes and a patient interest in yellowish stars. That is a useful perspective. Our Sun is everything from here, but from elsewhere it is a dot, and still that dot has planets. One of those planets has liquid water on its surface, a breathable atmosphere for creatures like us, continents that move, life that transformed the air, and minds that study the star that made their existence possible. The galaxy may contain many such worlds, or few, or forms of life beyond what we imagine. We do not yet know. But the Sun's place in the galaxy gives us one example of a star system where complexity arose. It shows that in a spiral galaxy, in a moderate region away from the centre, around a stable star with enough heavy elements, a rocky planet can become biologically rich. That is not proof of how common life is, but it is an existence proof. It happened here. When we think about the Sun's place in the Milky Way, we also think about night. The Sun dominates the day so completely that it hides the galaxy from us. Only when Earth turns away from it do we see the stars. In a lovely twist, the star that gives us life also prevents us from seeing the larger stellar family during daylight. Night is not simply the absence of the Sun. It is the condition that lets the rest of the galaxy appear. The Sun is our nearest star, but darkness reveals that it is not alone. Each night, if the sky is clear and dark enough, Earth turns us away from our own star and toward the wide community it belongs to. The Milky Way is not just scenery behind the Sun, it is the gravitational system that holds the Sun's long path. It is the source of the raw materials from which the Sun formed. It is the environment through which the heliosphere moves. It is the population of stars that gives context to what kind of star the Sun is. The galaxy is above and below the Sun in every direction once we step beyond local language. The Sun is embedded in it. There is no outside view from Earth, no simple top or bottom, only a position within a rotating disk and a path through a stellar neighbourhood. This embeddedness changes the feeling of the question we began with. What is above the Sun? The solar atmosphere, the corona, the wind, the heliosphere, and beyond that the interstellar medium and the galaxy. What is below the Sun? Its hidden interior, its core, its layers of radiation and convection, but also, depending on perspective, the galaxy beneath its path, the space through which it moves, and the gravitational structure holding it. Above and below are not fixed universal labels. They are invitations to choose a viewpoint and then look carefully. From Earth, the Sun is above the horizon. From the Sun, Earth is a small orbiting world. From the galaxy, the Sun is one star moving through the disk. From the universe, The Milky Way itself is one galaxy among countless others. The Sun's galactic place also reminds us that our daily lives are connected to deep history. The bread on a table depends on sunlight. The sunlight depends on fusion in the Sun's core. The Sun's core depends on the mass and composition of the star. The star's composition depends on previous generations of stars in the galaxy. The galaxy's structure shaped where the Sun formed and where it travels. A simple breakfast in daylight is tied, if followed far enough, to the evolution of the Milky Way. This is not abstract decoration. It is a chain of physical dependence. The ordinary world is made from cosmic history. There is a gentle humility in knowing that the Sun has a place, not the place. Ancient models often put Earth at the centre. Later models put the Sun at the centre of the solar system. Modern astronomy gives the Sun its rightful role, central to us but not central to everything. This does not diminish it. In fact, it may make it more beautiful. The Sun is not important because it rules the universe. It is important because it is the star that happened to gather our world into orbit, shines steadily enough for life, and carry us through the galaxy. Its importance is relational. It is our star. As the Sun moves through the Milky Way, the solar system comes with it, including every living thing on Earth. You have never been separate from that journey. Even when sitting still, you are travelling with Earth around the Sun, with the Sun around the galaxy, and with the galaxy through the wider cosmos. The motion is too smooth and vast to feel, but it is real. Every night of sleep happens aboard a moving planet in a moving solar system in a moving galaxy. This could feel dizzying, but it can also feel calming. You do not have to steer. Gravity has been handling the route for a very long time. The Sun's place in the galaxy is therefore not a remote fact. It is part of the setting of our existence. It tells us where our light comes from, where our star was born, what materials made our planet, what neighbourhood we travel through, and how our system fits into the Milky Way's larger structure. It stretches the idea of home. Home is your room, your street, your landscape, your planet. It is also the solar system, the heliosphere, the Orion Arm, and the Milky Way. The Sun is the bright centre of the smaller home and a travelling member of the larger one, and as this wider view settles, we can begin to draw the journey inward again. We have looked above the Sun into its atmosphere, below its visible surface into the hidden interior, outward through the solar wind, and farther still to its place among the stars of the galaxy. The Sun is not just a ball of light in the sky. It is a layered star, a magnetic engine, a source of wind, a traveller through the Milky Way, and the central influence in Earth's long story. What remains is to bring these scales together and ask what the Sun reveals about our own place in space and time, here on a planet that turns through daylight and darkness, while carried quietly around a star that is itself moving through the galaxy. The Sun reveals our place in time and space not by speaking, not by pointing, and not by announcing anything in a grand voice across the sky, but simply by being there every day, steady enough to become familiar and strange enough to remain impossible to fully exhaust. It is the object that turns space into direction for us, morning into beginning, evening into slowing down, winter into longing, summer into abundance, and a small rotating planet into a home with rhythm. We often treat the Sun as background, as weather, as brightness, as something to complain about when it is too hot and miss, when the sky has been grey for too many days in a row. But when we follow the story carefully, from the hidden core beneath its surface to the corona above it, from the solar wind moving past Earth to the Sun's path through the Milky Way, we begin to see that our lives are placed inside a much larger arrangement. We are not simply under the Sun. We are carried by it, warmed by it, timed by it, shielded and challenged by it, and made possible by the long history that produced it. Every sunrise is a local event, but it is also a cosmic one. From the ground, sunrise feels like the Sun climbing into view. The horizon brightens, colours gather, shadows return, birds begin, Windows glow, and somewhere someone who intended to wake up peacefully is startled by an alarm that sounds far less gentle than the turning of a planet deserves. Yet the sun has not climbed in any absolute sense. Earth has turned. Your part of the surface has rotated back into the light of a star that was already shining. This simple fact changes the meaning of morning. Morning is not the sun arriving from nowhere. It is Earth presenting you again to the star at the centre of our system. Each day is a rotation, a return, a repeated alignment between your small place on Earth and the steady flow of solar light. That daily turning gives us one of our most basic experiences of time, long before mechanical clocks, before calendars printed on walls, before phones quietly judged our sleep habits. People knew time through the sun. Shadows moved. Daylight lengthened and shortened. Seasons arrived and passed. The sun's position in the sky shaped work, rest, travel, planting, harvest, ritual, and memory. Even now, with atomic clocks and digital schedules, our bodies still respond to sunlight. Morning light helps reset the biological clock. Darkness allows sleep hormones to rise. The rhythm of waking and sleeping is tied to the rotation of Earth beneath the sun. We may live under artificial lights and glowing screens, but deep inside, the body still listens for the sky. The sun also reveals that time is layered. There is the time of a day, created by Earth's rotation. There is the time of a year, created by Earth's orbit and the tilt of its axis. There is the slower time of the solar cycle, as magnetic activity rises and falls over years. There is the far longer time of the sun's life, measured in billions of years, as it steadily converts hydrogen to helium in its core. There is the even wider time of the galaxy, as the sun carries the solar system around the Milky Way. When we say now, we usually mean the present moment in our own lives. But the sun reminds us that now sits inside many clocks at once. Your heartbeat, the day outside, the season, the activity of the sun, the age of the star, and the motion of the galaxy are all happening together. This is one reason the sun is so powerful as a guide to perspective. It does not merely give us light, it teaches us scale. A sunspot that appears as a small mark on an image may be larger than Earth. A magnetic loop that seems delicate may rise higher than many planets placed side by side. The solar wind that seems invisible fills a region extending far beyond the outer planets. The sun itself, enormous compared with Earth, becomes modest when placed among the stars of the galaxy. The galaxy in turn is only one among countless galaxies in the wider universe. Scale expands in both directions. We are tiny compared with the sun, yet the sun is tiny compared with the Milky Way. And still, the human mind can hold these relationships, at least gently, at least for a while before needing a cup of tea. The sun also reveals that space is not empty in the way it often appears. Between Earth and the sun there is a vast distance, but that distance is crossed by light, particles, magnetic fields, and gravitational influence. Sunlight takes only minutes to reach us, but it is part of a story that began deep in the solar interior. The solar wind streams outward constantly, shaping the space around Earth and the other planets. Magnetic disturbances from the sun can stir our planet's magnetic field and light the polar skies. Gravity holds Earth in orbit, not with a visible rope or rod, but with a relationship built into the structure of space and motion. The space around us is not a silent gap between separate things. It is a connected environment. That connectedness reaches into life itself. Nearly every living thing on Earth depends on the sun either directly or indirectly. Plants and algae use sunlight to build chemical energy. Animals eat plants or eat other animals that ate plants. Weather is driven by uneven solar heating. The water cycle depends on sunlight evaporating water and moving it through air and cloud and rain. Ocean currents are shaped in part by solar energy, interacting with atmosphere and rotation. Even fossil fuels, where humans have used them, are stored ancient sunlight captured by life long ago and buried through geological time. The warmth in a fire, the energy in food, the oxygen released by photosynthetic life, the movement of winds, the growth of forests, all of these point back toward the sun. This means the sun is not only above us in the sky, it is inside the history of our bodies. The energy that lets muscles move and thoughts form has passed through living systems, ultimately rooted in solar energy, except for some specialized ecosystems that depend on chemical energy from Earth's interior. Most of the biosphere is solar in origin. Your body is not powered by sunlight in the direct way a leaf is, but the food chain that sustains it is woven from sunlight. A simple meal eaten indoors at night still carries the trace of the sun. Bread, fruit, vegetables, grains, milk, meat, all of it belongs to pathways that begin with light and chemistry. In that sense, daylight does not vanish at sunset. Some of it becomes living matter, memory, movement, and warmth. The sun also reveals the importance of protection. From Earth's surface, the sun feels gentle much of the time, especially in the morning or late afternoon when light comes softly through trees or windows. But the sun is also a source of ultraviolet radiation, energetic particles, flares, and magnetic storms. Earth is habitable not simply because it receives sunlight, but because it receives sunlight through layers of protection. The atmosphere filters dangerous radiation. The ozone layer absorbs much ultraviolet light. The magnetic field deflects many charged particles from the solar wind. The distance between Earth and Sun keeps temperatures within a range where liquid water can exist over much of the planet. Life has flourished not by standing exposed before a star, but by living in a protected relationship with it. That relationship is finely balanced, though not fragile in a simple way. Earth is not a glass ornament barely surviving beside a furnace. It's a dynamic planet with atmosphere, oceans, geology, magnetism, and life all interacting. But habitability depends on many conditions working together. Too close to the sun, and water would be difficult to keep on the surface. Too far away, and the planet might freeze. Too little atmosphere, and heat would escape too easily. Too much greenhouse warming, and temperatures could rise dangerously. Too little magnetic or atmospheric protection, and the solar wind and radiation could have stronger effects. Earth is not just lucky because the sun shines. It is lucky because the sun, the planet, the atmosphere, the orbit, the chemistry, and deep time have all combined in a way that allowed life to persist and become complex. The sun reveals our place in space by showing us that home is not a single object. Home is a system. Earth is home, but Earth is home because it orbits the sun. The solar system is home, but the solar system is moving through the Milky Way. The sun's wind forms a bubble around the planets, a kind of extended solar environment. Beyond that lies interstellar space, filled with the thin material of the galaxy. The galaxy itself is home in a larger sense, because it supplied the elements from which the sun and planets formed. Home is nested, a room inside a house on a planet around a star inside a galaxy in the universe. The sun is the bright center of one of those layers, the one closest to our daily survival. There is humility in this, but also steadiness. We are not at the center of the universe. We are not even at the center of the galaxy. Our star is not unique in its basic nature. Our planet is small. Our lives are brief. These facts can sound cold if stated too sharply, but the sun softens them because it shows how deeply a small place can matter. The universe does not need Earth to be central for Earth to be meaningful. The sun does not need to be the greatest star for it to be our star. A small world can hold oceans, languages, music, science, grief, sleep, gardens, and people looking up. Meaning is not assigned by size. If it were, galaxies would be very impressive but very lonely. The sun also teaches that ordinary experience often rests on hidden depths. A patch of sunlight on the floor seems simple. Yet behind it is fusion in the core, energy transport through dense plasma, convection near the surface, magnetic activity, the escape of photons, the crossing of space, the filtering of Earth's atmosphere, and the rotation of the planet that placed that flaw in the beam. The ordinary is not less extraordinary because it is common. It is common because the universe has settled into patterns stable enough for repetition. Daylight is familiar because the sun is reliable on human timescales. That reliability is itself a wonder. When we look above the sun, we find atmosphere, corona, magnetic loops, eruptions, and solar wind. When we look below the sun, we find hidden layers, pressure, convection, radiation, and a fusion core. When we look around the sun, we find planets moving inside its gravity and wind. When we look beyond the sun, we find the Milky Way carrying it along with countless other stars. Each view corrects the one before it, not by making it false, but by making it larger. The sun is the warm disk in the sky. It is also a plasma sphere. It is also a magnetic engine. It is also a source of wind. It is also a galactic traveller. It is also the star by which Earth keeps time. The question of what is above and below the sun becomes, in the end, a question about perspective. Above and below are words born from standing on a planet with gravity pulling our feet toward the ground. In space, direction depends on where you are, how you are moving, and what reference frame you choose. Above the sun may mean outward from its surface into the solar atmosphere. Below may mean inward toward its core. Above may mean north of its rotational pole. Below may mean south. Relative to the galaxy, the sun can move above and below the galactic plane. Relative to Earth, the sun can be above the horizon or hidden below it. None of these meanings is the final one. They are tools. The sun teaches us to use them carefully. This is a quiet but important lesson. Human language is built for human scale. It handles tables, paths, weather, bodies, rooms, and rivers very well. It becomes less precise around stars, galaxies, plasma, and deep time. But instead of abandoning ordinary language, science refines it. It says, yes, the sun rises from our viewpoint. Yes, the sun has a surface, if by surface we mean the layer where visible light escapes. Yes, there is an atmosphere above the sun, though not like Earth's breathable air. Yes, the sun moves, though you do not feel it. Yes, space is mostly empty, but not inactive. The familiar words remain, but they become deeper. The sun also reveals that we live inside motion. Sitting still is real locally, but not absolutely. Earth rotates, Earth orbits, the sun moves through the galaxy moves through the wider cosmos. You may feel still in your chair or bed, but you are participating in all of those motions. You do not need to feel them for them to be true. This can be oddly comforting. We are carried constantly, not by intention, but by gravity and momentum. The universe is not waiting for us to push it along. It has been moving us all our lives. There is a tenderness in the fact that our bodies evolved under one star. Our eyes are adapted to the kind of light that reaches Earth's surface. Our sleep is shaped by day and night. Our skin responds to sunlight. Our calendars follow the year. Our moods often shift with seasons and brightness. Human culture is filled with solar meanings because the sun has always structured life. It marks beginnings, endings, harvests, journeys, celebrations, and rest. Even when we study it through advanced instruments, the sun remains the same familiar presence that warmed the earliest humans and guided their sense of time. At the same time, the scientific sun is not the mythic sun, and that is good. Knowing the sun is a star does not diminish sunrise. Knowing that fusion powers it does not make sunlight less beautiful. Knowing that Earth turns rather than the sun rising in a literal sense does not make morning less real. Explanation and wonder are not enemies. A rainbow does not become dull because we understand refraction. An aurora does not lose beauty because we know about charged particles and magnetic fields. The sun does not become less majestic because we know it is plasma. It becomes more intimate because understanding gives us more ways to belong to the scene. The sun also places us in deep time. It was shining before humans existed, before mammals, before flowers, before the continents took their present shapes. It shone over ancient seas where the earliest life changed the chemistry of Earth. It shone over forests that became coal, over reptiles that vanished, over ice ages that came and went, over the first tools, the first fires, the first stories told under night skies. It shines now over cities, deserts, oceans, farms, satellites, telescopes, and sleeping villages. It will continue after us, changing slowly, carrying Earth forward into futures we cannot fully imagine. Our lives are brief, but they are lit by a star with a long memory, written not in thoughts, but in physical continuity. This can make a single day feel more precious. A day is ordinary because there are so many of them, but each one is also a complete turn of Earth into and out of sunlight. Each morning is a return to the star. Each evening is a turning away. Each shadow is a small geometry of light and matter. Each season is the planet's tilted journey around the sun. When we understand this, the calendar becomes more than a schedule. It becomes a record of motion through space. Birthdays are not only marks of age, they are completed orbits. Anniversaries are returns to a similar position around the sun, though the sun itself has moved onward through the galaxy since last time. Nothing returns exactly, and yet patterns repeat closely enough for memory. The sun's place in the galaxy gives another kind of comfort. Our star is not isolated in emptiness. It belongs to a vast community of stars, many with their own planets, many with histories we're only beginning to understand. The atoms that form the sun were shaped by earlier stars. The materials of Earth came from galactic history. We are not separate from the universe looking out at it from a distance. We are made from it, born inside it, and aware of it from one small location. The sun is one of the bridges between the universe and us, because it gathers cosmic material into a stable star system and pours energy into the world where awareness arose. And awareness matters here. The sun does not know it is shining. The corona does not know it is beautiful. The solar wind does not know it is touching Earth's magnetic field. The galaxy does not know it contains us. But we know, at least partly. We can trace the path of sunlight. We can model the solar interior. We can send spacecraft into the solar wind. We can watch the sun in ultraviolet light. We can measure the motion of stars. We can ask what above and below mean in a universe without a universal up. This capacity is not separate from nature. It is nature in one of its more reflective forms, trying to understand the conditions that made reflection possible. Perhaps that is what the sun reveals most clearly. Our place in time and space is not central, but it is connected. We're connected to the sun through gravity, light, energy, climate, biology, and timekeeping. We're connected to the galaxy through the sun's origin, motion, and chemical inheritance. We're connected to deep time through the long stability of a star that has allowed life to grow complex enough to study it. We are connected to the future because the sun will continue to shape Earth's fate long after this moment has passed. To understand the sun is to understand that we are part of a chain, not floating separately in meaninglessness, but held within relationships. So when daylight returns, or when you remember it from the quiet of night, the sun may feel a little different. Not just a bright disk, not just weather, not just a symbol of morning. It is a star with hidden depths below its surface and a restless atmosphere above. It has magnetic threads that rise and fall, a wind that fills the space around us, and a path through the Milky Way. It is ordinary among stars and extraordinary to Earth. It is distant enough to be safely far away and close enough to shape nearly everything we know. And now, wherever you are listening from, Earth is still turning. Somewhere the sun is rising. Somewhere it is high overhead. Somewhere it is setting. Somewhere it is hidden beneath the curve of the planet, waiting for morning only because the world has not yet turned that way. the sun itself continues shining, not hurrying, not pausing, not concerned with our clocks, but giving us the light by which we invented clocks in the first place. If this quiet journey has helped you rest, or given the evening a little more wonder, I am glad you came along. The universe is large, the sun is restless, Earth is moving, and for now, in this small moment of space and time, you are here, beneath the shelter of a turning world, carried gently around a star.